I think you have to be,
Yeah, I think only one person can stream it at a time.
but you could record it and then upload it. So
Yeah.
Somebody needs to do an audio check. I just noticed that the slide deck James sent out, the Slack links for Windows Help and stuff is to the old Slack. It's not to the new Slack.
if you give it to me in the chat, I can replace it right now. I thought that we were using the same Slack.
You say it again, please?
I thought we were using the same Slack.
That wasn't the plan.
Can somebody check? Because people have been registering. Have they been registering the old one or the new one?
Registering a new one. We have about 90 people on the new one.
Okay, please send me the link and I'll fix it. Yeah, thank you. Jim, did you get it? Or Juliana, Juliana, do you have the link for the correct one? I'll fix it now.
Giuliano, should we make help channels on the Slack for Windows, Mac, and Unix?
Yep, good idea.
Okay, TJ, is there anything else you want me to do now?
I think we're good to go.
Okay. Well, welcome everybody. We'll just take another minute or two. We said we'd start at 10:10, and the official meeting starts at 10:30. And so we've tried to create a half an hour before the meeting begins and a half an hour after the meeting ends to open up discussion, allow people to ask questions, do problem solving informally, and to give you a little bit of an outline of what the plans are for the day. I'm James Glazier. I'm one of the instructors for the class. I'm very pleased that you've come here today, and I hope it's going to be a productive week or so. And I would appreciate very much your coming. I know people spend a lot of time coming to do this, and I hope that you all get a lot out of it. So with that, I guess, shall I start, TJ, or do you want me to wait another minute or two? I guess we said 9:10, so I'll wait another minute. Okay, welcome everybody to the very first piece of a long 9-day marathon where we will look at CompuCell modeling. Today is a review of Python, basic Python, focusing on what you need to be able to write CompuCell models. And we hope that it's productive for you. If you haven't used Python before, I hope it will help you get started. If you have used Python before, then it should be mostly a review. I need to tell you that this meeting is live streamed on YouTube and is being recorded. So please be aware of that. I had originally had the wrong Slack channel posted on the title slide. The correct one has been put into the chat. If you have any trouble getting onto the Slack channel, please let us know. The basic outline of the course is today we're going to have every day is going to be 4 modules, each one of an hour and a half in length. Today is day 0. We're going to start off with Python basics, then talking about slightly more complex data types in Python, and then specific things that we use a lot in CompuCell, in particular dictionary, and end with classes and attributes. Tomorrow, we'll have a basic introduction to CompuCell and do some simple simulations. Day 2 will be about forces and chemical fields. Day 3, we'll use those to begin to build more complex models and begin to talk about how to do subcellular modeling. And then day 4, we'll focus on subcellular modeling. And day 5, we'll talk about extensions to CompuCell to handle solids, philopodia, and more complex systems. Then days 6 and 7, which would be the following weekend, will be the hackathon. We hope you'll participate. Again, the structure of the class will be, we'll have informal discussion now until about 10:30. So if there are any questions or troubleshooting you need before we get started. TJ, I don't know what environment. Are you using the NanoHub Jupyter as your IDE for this?
Yeah, today we'll send everyone to the Tellurium app, and we'll just work from there.
Okay.
And we'll start pretty early on with an overview of getting everyone started there.
Great. And then we'll have a short break between noon our time, which is Indiana time, and 12:15. Second module, again, an hour and a half, then a half an hour lunch break. Third module, short break. Last module, which has a typo in it, which I'll fix in a second. And then a little bit of wrap up and discussion if people have any issues or questions that they want to address. All of the videos will be put up on YouTube, and also once they're cleaned up and edited, will be made available in the student materials folders as well. Zoom logistics, in general, screen sharing and microphones will be disabled. If they're not, please remember to keep your mic muted when you're not talking. Feel free to use the buttons, faster, slower, need help, and so on. We have a set of breakout rooms where you can go for one-on-one help if you want. I want to remind people about the hackathon. The hackathon will be a week from this weekend, Saturday and Sunday. And it would be helpful. I was going to actually do a formal poll, and I'll repeat this tomorrow. But if people could just do a show of hands, if you can click on the raise your hand button, if you're thinking you might participate in the hackathon, you don't have to be committed. But it would be very helpful to us if we can get a sense of what fraction of people want to participate in the hackathon. Okay, so if you're interested in doing the hackathon, we very much ask you to give us one slide on your hackathon idea that we can show on Tuesday and have you present. And we also have a Google Doc where you can upload your idea. And the reason for this is that we'd love to help you team up. And the more time we have to help people team up before we start the hackathon, the easier it is to do. So I will reshare those links in the chat in a minute. But in the past, those have been very productive. Several groups that have started hackathon projects have wound up publishing the work that they did. You don't have to have an idea to participate in the hackathon. In other words, if you want to participate in the hackathon, but you don't have your own idea, you should look at the other people's projects and see if there's one you want to join. The idea is to try to team people up and build teams, especially if you have complementary experience. Somebody's a wet lab biologist, somebody's a clinician, somebody's a mathematical biologist, somebody's a computer person. Those kind of teams work really well. And so we definitely would appreciate help getting that organized. We've blocked out 2 1.5-hour modules during the coming week to help people team up for hackathon work. We may not need all of that time, but if there are plenty of people who want to do the hackathon, we want to make sure that we get that set up appropriately. So please help us out on that. Again, there are links. The main links you need to know for reference are going to be the Multicell 3D webpage and the NanoHub CC3D app. TJ, if you want me to add this to the slide deck, that you're using the Jupyter app or the Tellurium app? You said Tellurium app. I'll add that to the slide deck. And we don't need the Multicell desktop code at the moment. The resources I posted mostly online already through the chat. Again, if people are having trouble finding anything, let us know. The Slack channel and the joining have been posted, and I hope people are able to get in. Jim Sluka is here to help you if you are having trouble. So message James Sluka through the chat if you're having any trouble with the Slack now. The main people you're going to be hearing from this week, myself, James Glazier. TJ is taking the lead today. He'll also be speaking later in the week. We're going to have talks and assistance from Professor Gilberto Tomas from the University Federal do Rio Grande do Sul in Brazil. Normally he'd be here in Bloomington with us, but this year he's participating remotely. Professor Giulio Belmonte for North Carolina State University is going to be giving quite a few lectures. Giuliano Ferrari Gianlupi is going to be lecturing and also helping out here from Indiana. Jim Sluka, also from Indiana, will be lecturing and helping out. Joshua Pontes Serrano from Indiana will be lecturing and helping out. Professor Bobby Matamachi from University of Michigan will be helping in various ways. We'll see him from time to time. And Lorenzo Vischini has very generously agreed to help out. He's taking the course, but he's also helping. It's very kind of him to do that. And there's also Pedro Castel from Brazil will also be available to help for some of these. If you happen to be more experienced and you'd like to help out, especially during the early sections, we'd appreciate that. We have a big class and we want to make sure that everyone gets plenty of attention. With that, I'm going to turn it over to TJ. I know it's a little bit early. If you want to put up your splash slide, and then if there are any questions, we can answer them. One thing that I was going to ask while we're waiting, it could also be a show of hands, is how many people in the class have done either took Herbert Sauero's class in network modeling using Tellurium 2 weeks ago. Did anybody take Herbert Sauero's class 2 weeks ago? Trying to see that. If so, if you could raise your hand. Of course, people may have raised their hand about the people know how to take their hands down in Slack once you've in Zoom once you've raised it. I just was trying to get a rough sense of how many people might have had exposure to Tellurium type modeling before. Have people done any kind of network modeling using another package besides Tellurium? No. Okay, TJ, it's over to you then.
Okay, James, would you like to start early or give everyone till 10:30 our time to arrive, or?
I would definitely wait and not start till 10:03.
Okay.
The official top of the hour these days is three minutes past, I think.
10:33 it is. Okay, well, I guess we can leave this time open for any more questions or any support to get started for the day and the week. That's okay. Oh, James, you're muted.
Yeah, sorry, I hit the unmute. Somebody asked an excellent question, which was somebody had not taken Herbert's class on network modeling, and they asked if it was useful to watch the videos on YouTube. It would be very useful to watch the videos on YouTube, and if you send us the link, we can definitely make sure that there's a link in our materials to those videos. Because I knew that Herbert was recording them, but I didn't know that what the video channel is. Jim, do you have that? I'm going to add that to our reference list. That's great. Thank you very much. We'll put that into the reference materials. That's extremely helpful.
Okay, I'm gonna step out for a minute. I'll be back well before we start though.
Are there any other questions before we get started? We'll be ready and we'll be starting in just a few minutes. Somebody says, I didn't take the course, but I brought and read the systems bio book that was suggested. Is that enough? That should be plenty. We're going to do some to build complex models, one needs to know quite a bit, but the integration of Tellurium with Compusol is very simple. And so the amount that you're really going to have to know in advance to be able to do the integration is quite limited. To be able to design complex models is an effort. And so I definitely would say that if you want to go forward with this in your work, probably reading that book is a good idea. But it's a great introduction. Herbert's textbook is excellent. Any other questions or comments that you'd like to make? How somebody said Herbert used the Colab implementation of Tellurium. How did that go? Was that productive? Yeah, we're planning on for next year having Colab versions of things as well. TJ, while you were away, there was a comment that Herbert used a Colab installation of Tellurium this year, which makes sense. The NanoHub installation and the Colab installation will look almost identical. And for today, if you wanted to use the Colab one, that would be fine. It's not going to have any differences really from the NanoHub.
Yeah, by and large, the the work that we'll do will be Python only. We'll use the Tellurium Jupyter notebook. We may, use some libRoadrunner functionality or so on and so forth, but by and large, we'll keep our work today restricted to Python only. So it's, if someone wants to use a different IDE or something else, that's also totally fine.
For the people who want to participate in the hackathon, were you able to find the links to the folder to upload your hackathon slides and your ideas to the Google Doc? I'll post those in the chat again. If anybody has any trouble, please contact me. I'll give you my email address again. If you have trouble with that. No, if you want to join somebody else's project, So if you want to join somebody else's project, you don't have to have a slide, and you can make up your mind at the last minute too, and you can come up with new projects between Tuesday and the hackathon. It was just that we wanted to have people have the opportunity to do a short lightning presentation of their ideas on Tuesday, so that people could see them, and if they need it, they can do it. Yes, the idea was that people would upload a PowerPoint slide, which we would show on Tuesday and people could talk about. And we would also separately have a Google Doc where people could type paragraphs describing their ideas. That's why we're, in a sense, we're asking you to do the same thing twice in a different format. Okay, I'll get out of the way. It's time for me to let you start.
There we go. All right. Yeah, we're close enough. Let's go ahead and get started. Well, thank you all for being here. I won't continue with the introductions so much, but just say that I'm very glad to be here today. Very glad to have all of you here to work with us for the week. As James said, my name is TJ Sego. We'll be working together for all 4 modules of the day for today, and all on a crash course introduction to Python programming. Now, a lot of what we will learn today will be specifically geared towards working on Compusel in Python. So today's modules will be by no means exhaustive. The goal is not to make experts in Python out of all of you, but rather to get you to a starting point where when we start on the workshop beginning tomorrow, there are no deers in the headlights, so to speak, but that you can follow along, build models along with all of us as we're going through the various modules for Compusel, and then hopefully in the hackathon to actually go off and work with your peers to work on your own projects while we roam around and support. So Python is a great programming language for a lot of reasons. In scientific computing and in computational modeling, Python is widely used for a number of applications in biological modeling. For those of you who took Herbert's course, by now you're probably quite aware that Python is used very extensively for doing network modeling. Python's very good for being able to take, say, implementations of existing models and adding new models to them. So modifying things that, say, others have developed that you would like to contribute to and adapt and improve or work from. Python's also great for doing analysis of experiments. So it's very straightforward to get into doing analysis of large data sets, doing visualization, statistical analysis, so on and so forth. Now, today we'll focus on just the very basics, and admittedly, there are basics about Python that we will not cover today. So today is almost exclusively reserved for supporting the Compusel workshop. I would like to note that for those of you who may be interested in learning more, that we would be happy to provide additional learning resources. So there's a lot that can be done with Python in a lot of different applications. And if you're like me and have an interest in using software to do computational modeling in science, and would like to know more about where to find some of those resources and so on and so forth, you can send an email to one of us or enter into the chat or into the Slack channel, and we can connect outside of today's class. Just as a quick reminder for those of you who may have missed the pre-module informational session today is being live streamed and recorded. So you are live on YouTube currently, and we'll also be recording this for reference as a learning resource for people going forward into the future. So just want you all to be aware of that. Now, I wanted to kind of start today with a couple of overarching points to sort of set the tone for today and make sure that everyone has a good sense of what to expect of what they learned today, what to expect from themselves with learning how to do programming using Python, and also from a logistical standpoint, what happens in the case of, say, loss of internet connection, practically speaking. So there's always the chance that I may get disconnected intermittently. I've in the past had intermittent internet connection issues. If that happens, just hold tight. Giuliano may pick up. Otherwise, just hold tight and I'll be back with you very shortly. Now, concerning our actual learning experience today, it's important to know that no one who works in software development knows everything about the software, programming language that they use. And so one thing to always expect when going into using programming to develop software is to always expect that you're going to have to learn something. Never expect of yourself that you should know everything about the language that you write in. There's always an element of learning something new. Something is always being developed, especially in a popular programming language like Python. Something new is developed every day. So there are always new tools. There are always improvements to existing tools. So you should always expect that you will be far from knowing everything, and that working on any project most likely will be, at least in some sense, a learning experience. And that may be even the case today. We may see this today where someone may have a question that I just don't know the answer to, and that's perfectly fine. We have lots of resources. The internet is our best friend in that regard. And so always expect this to be a learning experience. The internet is the best place for finding information to accomplish the things that you want to do. If you don't know how to do something, there are plenty of resources. Every decent package comes with at least decent documentation, Compusel included. And so if you don't know how to use something, documentation online that's developed by the developers, are always a great resource to figure out how to do something with something that's been developed and made available. Other coders in the world are quite generous with their experience. You'll find that if you go to, say, stackoverflow.com, you can find lots of answers that have been submitted by other software developers answering specific issues. So something like, something like a Reddit channel where you can post questions and other developers can answer your questions. It's an invaluable resource for software developers, is to have that community of advice and experience that's given by their peers. Now, almost always when developing, some sort of solution in software in general, this is true in Python, in C++, in Java, and just about everything. There's almost never a unique solution to what you may want to accomplish. So because of the level of abstraction and the degree of functionality that comes with a lot of languages like Python, just about any time that you set out to do something, you'll find that you can generate lots and lots of different ways to do it. And so what's important to always keep in mind when developing software solutions, even for just very basic code, is to always focus on what you want to do. How you do something is never going to be unique, almost never going to be unique. And so what's important is to focus on what you want to do and experiment with different ways of doing it. You'll find that two coders trying to accomplish the same thing will go about it in two, say, similar ways, all the way to extremely different ways. So what's very important is to keep in mind the actual, functionality that you're trying to accomplish, the tasks that you're trying to accomplish with your software, with the code that you're writing. And probably most importantly is that, in my opinion, the number one key to success in software development is perseverance. Software can be maddening. For some of us, developing software is an emotional experience at times. And what's most important is, that you keep strong, you keep calm, break things down, say working on a complicated task, break things down into, say, simpler tasks, and use the information that's available to you online, use the documentation that you have at your disposal, all the way to very basic textbooks, or YouTube videos like the one that we're making right now, and just hang in there, try things out, and you'll get there. So with that, let's start doing stuff. For those of you who don't have any sort of Python environment set up on your local computer, we're going to refer to the Tellurium app as discussed in the pre-day informational session. So we're going to migrate over to NanoHub. I'm going to split my screen here, and we're going to do a little bit of work together. So let's start by migrating over to NanoHub. If you're not there already, we're going to go to the NanoHub Tellurium app. I will put the link in the chat. There's the chat. The link in the chat for everyone. That will take you to the web page that you see on the left-hand side of my screen. So this is the Tellurium app. The Tellurium app is a Jupyter notebook that has Python and Tellurium. We, by and large, are not going to work with Tellurium per se, but more so work in the environment that's been set up for Tellurium. So everyone would like to start by following that link. If you've not set up a NanoHub account by now, then you should be prompted to create a NanoHub account that looks something like what's in this screenshot here on the right-hand side of my screen. You may have to click the Launch Tool button on the Tellurium tool page to get here. But for those of you who try to launch the Tellurium tool and haven't created an account, you should find something like this. You can also just select the sign up button on the main NanoHub landing page, which is just nanohub.org. And you can follow with whatever sign-in credentials you'd like to generate. Fill out a username and a unique password. Give everyone maybe just another minute or so in case not everyone has done this yet.
You want to use the poll to check if people are all into Tellurium?
Yes, let's do that. Looks like we've got a few people who still need a little bit more time. And of course, if anyone runs into any technical issues, please let us know. We can put you in a breakout room with either Jim or Giuliano to help get you back on track and along with the rest of us. Someone asks, can I just do this on Jupyter Notebook on my local host? Absolutely. So we'll start with a very quick example that does use Tellurium, but that is just for those who are not familiar with using Jupyter Notebooks. So if you have a setup locally and want to use that, by all means.
Or again, if you took Herbert's course and you have a collab version of Tellurium, that would be fine too. Is anyone else having trouble with the NanoHub launch?
Remember that people can't unpost to the survey.
All right, looks like we're going to do this again. Let's check in with everyone, see, make sure everyone. Yeah, there we go. Make sure everyone is with us so far. All right, looks like we're good. So let's continue. Appreciate everyone's patience. We've got quite a few of us. We want to make sure that we don't lose anyone along the way. So thank you very much for hanging in there. So for those of you who are using Jupyter Notebooks in some form or another, if you've not used Jupyter Notebooks before, we're just gonna crash through how to use this for executing Python code very quickly. So in Jupyter Notebooks, every one of these little boxes is called a cell, and each cell consists of an executable section of code. So you can write whatever you'd like. And in these cells, you put some Python code, and then when you would like to execute it, you just press Shift Enter. So when your cursor is in an active cell and then you'd like to execute it, just press Shift Enter and you'll get a result. Now there's all sorts of other things you can do with this. You can say click on a cell and click on Edit and delete cells. And in the case of the Tellurium app, that'll reset everything all the way back to just this first statement, which is to bring the Tellurium app into the executable code. So we execute things that we put in our cells by pressing Shift Enter on our keyboard. Now for the case of the Tellurium app, if you're using NanoHub and the Tellurium app, the notebook that launches, so that opens when you launch this tool, is by default read only. This cannot be saved. And so in general, if you would like to store your work using the Tellurium app, whether today with keeping our exercises on your local machine for reference or when working on something else, what needs to be done is to take this default starting notebook that's read-only and then make a copy of it. And in NanoHub, you can make a copy in a drive that's yours. And that copy, you can save, edit, download, so on and so forth. And so you can do this by, in the NanoHub tool, clicking on the menu bar, clicking File, and then select Make a Copy. And Now you should notice in the top, in my original launch, at the very top next to Jupyter, it just says Tellurium with this note that says read only. Now when I selected make a copy, a new tab was opened, and now I see this file is called Tellurium-copy1 with no note about being read only. So this is now a notebook that I can save. Now you can do saving procedures, downloading, and so on and so forth in the file menu as well. We're going to start by actually doing a very quick little example. So I'm going to put another link in the chat. This, again, is only for those who are using the Tellurium app. So you can follow this link to the documentation for Tellurium. We're just going to grab a little bit of code off of the Tellurium site. We're going to put it in one of our cells, and we're going to execute it. Oh, I'm sorry, was there a question? Okay, no problem. Yeah, so link in the chat. This is to read the docs for Tellurium. So this is the online documentation. I have this pulled up as well. Now on the left, if you click the link for Quick Start, this will take you to the Quick Start page. And what we're going to do is we're going to select these 3 lines of code in this first sample called Simple Example. I'm just going to select all 3 lines of code and copy it and see if we can paste that into our Jupyter notebook like so. For those of you who didn't take the Tellurium course, this is just specifying a very simple ODE model, simulating it for a number of simulation steps, and then plotting it. And that's all we're going to do. So again, the link to this page is in the chat. We're going to copy the 3 lines of code under Quick Start and Simple Example. We're going to paste those into our Jupyter notebook and then execute it by pressing Shift-Enter. Now I get an error. I get an error. Let's see if we can fix it like this. Now you notice that I missed the first line of the code and ended up getting an error. It happens, and it happens all the time. We're going to see errors all day and all week. Totally fine. Said that it was missing something called TE, and that was because I forgot to copy the first line, and this did not carry over from the first cell. So when I fix that, then I have what's provided in the Quick Start manual page from Tellurium. So with all 4 lines, we should have something like this. Tareen points out in the chat that it could have just rerun the first cell. That is correct. So in Jupyter Notebooks, the execution of cells occurs sequentially from top to bottom based on what's been previously executed. And in this case, I have not re-executed my first cell. We're going to try to keep our work today as basic as possible concerning actually utilizing multiple cells. Jupyter Notebooks provides a ton of additional functionality for lots of interesting things. And so what we're going to try to do is keep all of our code that we execute for today's exercises all into individual cells. Yes, question, does run all work for doing multiple cells? Yes, it does. So shift enter will execute a cell, and then, yeah, under cell in the menu bar, if you click run all, then that will go from the top and go through and execute every cell from top to bottom. All right, so let's try this poll again real quick. Make sure everyone's with us. It's not critical that we have a strong understanding of the particularities concerning tellurium right now. Probably what's most important is that everyone can get something into a cell, preferably the example provided in the tellurium documentation, and can execute the cell and generate a plot. So James, can we restart this poll and make sure we haven't lost anyone along the way before we continue? Thank you. Polly asks if it's possible to save notebooks locally. The answer is yes. So you can save this to your drive on NanoHub, and then you can also, in the file menu item, you can go to download as, and you see you actually have quite a few options. So you can download this locally as a notebook. You can also convert this to raw Python code. On NanoHub, you can save this as save and checkpoint. So again, that's in the menu bar as well. Under the file menu item, click save and checkpoint.
Somebody's asking for help. Could you raise your hand and if you need help?
Looks like there's also some questions about the model specification here. So this is antimony model specification. What this says is that as a species S1 converts to a species S2, and that occurs with the rate proportional to K1 times S1. And for initial conditions that aren't specified explicitly, as in for S1 here being declared as starting at 10, if no declaration is made for initial conditions, then the value is assumed to be 0. So not critical for getting through today, but we will spend, I think, half of a day working in this world. All right, so it looks like we have someone who needs some help. Have we connected them with someone yet? Or we have break rooms set up?
So okay, I'll put them in a breakout room.
All right. So I'd say let's continue then. If you've not gotten to this point entirely, that's okay. We'll have lots of practice getting code executing, and lots more practice at dealing with errors, both today and through the rest of your career as Python developers. So let's start with a first very basic example, and I'm just gonna do this interactively along with you. You can, again, reset your notebook by going in the menu bar to edit and delete cells. For the Tellurium app, that should just reset it to having the import statement at the beginning. And we're gonna do a very basic exercise of doing an actual calculation. It's not super important that you understand how exactly all of this is working, but we're just going to do a basic calculation of adding two integers, and we're going to do this like follows. So let's say that we have two integers, and we're going to call them a and b. And let's say that a is equal to 1. In Python, you can just start by naming a variable. Here's a, and just declaring it as equal to 1. Python will understand that as an integer. And let's hit enter, and let's say b equals 2. So we have a second integer b, and we're going to say that's 2. And then our third integer we're going to call c, and maybe you guessed it, c is equal to a plus b, and that is just as simple as exactly typing that. C is equal to a plus b. And if you'd like to see the output of that calculation, we'll review this more later. So not super important to understand it now, but just for now, believe me when I say that you can type print parentheses c. So a equals 1, b equals 2, c equals a plus b. And then print c. And then we'll execute it. And what do you know? We get a 3. So you'll notice here that in Python, this is as simple as just naming something and just telling Python what it is. In this case, we wanted to assign simple integers to names of variables that we can then later refer to by name when doing subsequent calculations. And we can name the results of those calculations and assign them to variables according to how we name them. In this case, saying that the result of our named variables a and b, we'll name that and assign it to a variable called c, and then tell Python to do something with the variable that we assigned the result to, that here being c. And in this case, just doing something as simple as printing it to screen. And that brings us to the very basics of what are called types. So in various programming languages in Python, you have lots of different ways that we can represent data. And in the very simplest case, we can take data and assign it a particular type for a representation of a particular piece of data. In this case, we just said that we had two integers equal to 1 and 2, and we were going to represent that data in our executable software using the variables named a and b. And when we do this, somewhere in memory on our computers, the integers 1 and 2 are stored in memory, and we can refer to them by the names that we've assigned to them using these assignments. Now, scalar types are types that work with single pieces of data, but those can be different types of data. when you consider, say, the difference between 1, the integer 1, and something like 1.1. Or say, consider the difference between the integer 1 and say the character A. In Python, these are treated differently, and these are all called scalar types. So these types of data that are scalar, most importantly, cannot be subdivided. So when you have a single piece of data like an integer or say a string of characters, those can't be divided up into say sub-elements of data, and hence they're referred to as scalars. So to get us started, scalar types that are available in Python for numbers and booleans, we have integers, which are just called int, int. So here A, B, and C, all of these have a type called int. Whereas say a variable that's been assigned a real number like 1.1, 5.1, 7.6, anything with decimal precision is called a float. So there are ints for integers, there are floats for real numbers with decimal precision, and then there are Boolean value types that are just referred to, they're called bool. So you can have a variable, say D equals true, or E equals false. And D and E here are Boolean valued, and they are called, their type is called bool. So you can see what some of these look like, or you can check the data type of a variable. I'm actually going to switch out of Jupyter Notebooks and switch over to my favorite IDE, which is PyCharm. So here, say we have a variable D equals true. D here is a Boolean, and we can find that out by using a function type. We can say type parentheses and give it a variable. And when we print this, we'll find that Python will tell us that our type of our variable D is a bool. And you can find that you can do this the same for, say, D equals to 1. You get that it's a type int. D equals 1.1. Now it's a type float. Now it's possible to take data and actually convert it from one type to another. This varies in mileage based on the types of data that one is trying to convert from and to. So in some cases, it's possible to convert data from one particular type to another. In other cases, it's not possible at all because the conversion is not defined. Now that conversion is called casting or type casting. And in Python, for simple scalar types, it's possible to do something like the following. So say we have an integer A equals 1. And say we would like to have another variable B that is equal to A, but instead of it being an integer or an int type, we'd like to have it as a real number or a float. We can do this by doing something like this. B equals float A. And we'll find that when we print A and print B, my first entry of the print just shows a 1, and that's A. And then my second print shows 1.0. That's a float. Now it's possible to do the same for the other scalar type that we've already discussed, being the bools. So in this case, you'll have something like C equals bool of A. And this is a first example of particularities concerning the conversion of types from one data type to the next. If we say convert our integer a, which is equal to 1, if we cast that to a bool and assign it to c, what would we get for our value c? What is 1 interpreted as? 1 being an integer, what is that interpreted as in Python in terms of bools? And we'll find that in our third print, if we print c being equal to the bool of a, we get that it's equal to true. And we'll also find that if, say, we were to change a equal to 0, a would still be an int. And we'll find that if we cast a to a bool and assign it to c when a is equal to 0, now we'll find that the cast is equal to false. And so in the very simplest, but of many different types of typecasting conversions, the convention is, in this case, that for integers, when casting an integer to a bool, we'll find that if the integer is equal to 0, that's understood as being false. Whereas if an integer is non-zero, is always interpreted as being true when cast to a Boolean. And there are lots of particularities concerning this. I see in the excuse me, in the chat, there's some discussion about rounding issues and what happens when, say, casting from an integer to a float or vice versa, along with particularities for that very common typecast. The list is endless of the details for casting data from one type to another. Python being among the simplest languages to do this in. And so what's most important here for our case now is that it's possible to convert data from one type to another, and that those conversions occur according to specific rules. For the case of our built-in types, our scalar value built-in types like the int, the float, the bool, those all have predetermined rules for converting from one type to another, most of which you can typically just figure out just by simple experiment, like what we've done here. For complicated types, the complexity can be endless. Now, we've already done a little bit of this, but in Python for writing expressions, in particular for mathematical expressions, expressions read from left to right according to order of operations as one would expect. So when doing basic mathematical calculations, like in our very simple case of when C was equal to A plus B, this simply just reads from left to right, A plus B. Whereas if one, say, doing more complicated calculations like A plus B, take that sum and multiply it by B, this follows the normal order of operations in that A plus B is first calculated and the sum is then multiplied by B. And Python provides all of the operators that one would expect for doing basic calculations for the case of addition, subtraction, multiplication, and division. These are accomplished as one would expect. So if A equals 1 and B equals 2, you can do all sorts of operations like A plus B for addition, A minus B for subtraction, for multiplication, A times B, the multiplication symbol being the asterisk, and A divided by B using the slash, and then two additional operators of interest. The first being calculation of the remainder. And the remainder operator is the percent symbol, and this is the remainder of A divided by B. Or if you were looking at the slides on my right, this would be the remainder of I when divided by J. And then lastly, for very simple operators, there's the power operator, and that is to take A to the power of B. In Python, the power operator is the double asterisk. So when taking A to the power of B, write A asterisk asterisk B. Now, Python is not particularly picky about spacing for the case of doing simple arithmetic like this. So A equals 1 with or without spaces in between, both are equally valid. Spacing becomes more particular and much more particular when we get more into control structures, which we will get to today. But for now, while I tend to find it a little stressful to read code that has no spaces in between operators, putting spaces in between or not, both are equally as valid for doing arithmetic operators.
Hey, TJ,
Jim,
put a space in front of your first line and run it.
error.
Yeah. So Jupyter doesn't handle spaces correctly. Because if you do that in Jupyter, it doesn't throw an error.
It does not.
And I tried idle as well. Idle also throws an error. And I could have sworn that that's serious Python-S, is that those spaces absolutely positively always matter. So it's interesting Jupyter doesn't catch it. Anyway, okay.
Yeah, so in the case of having preceding spaces that may or may not produce errors depending on what's actually parsing the code, has everything to do with, in Python, the way that control structures are constructed is using indentation. And we'll visit this a lot more later, but putting sort of like erroneous spaces before the beginning of a certain line of code can confuse Python very quickly, because Python actually uses preceding spaces to understand your intentions concerning the actual flow of your software. In a very simple example, writing a block of, say, conditional statements of if this, then do that, so on and so forth, can look in Python like this. Python will understand this, with preceding or with successive layers of control logic based on the actual indentation. So if you find yourself putting lines or spaces before your lines of code and getting seemingly strange errors, this has everything to do with that Python very much cares about the spaces you put before the beginning of your line of code. Now, once you actually start writing the code, that so much doesn't matter. At least not for operators like this. All right. Let's continue. Yeah, as mentioned, ordinary order of operations apply for doing arithmetic calculations. Now, we've been doing this for a little bit now today, and that is assigning variables. So again, you want to take a piece of, say, data and actually assign that into the memory of your computer for subsequent calculations or processes. We do this just by, in Python, just declaring a name of a variable and then assigning it some sort of value. This can be done successively for the same name. A equals 1, A equals 3, A equals 5. You'll see my IDE is showing me warnings saying, basically, what are you doing? But this is all valid. This can get more particular for more complicated data types, but for the case of floats and spools, this is all perfectly fine. Now, one thing to note is that when doing a set of calculation, like a procedure of calculations, is that variables that have been derived, their values that have been derived from actual calculations, don't necessarily automatically get updated if they've been calculated from other variables. And what I mean by this is that in our very simple example of adding two integers, we had A equals 1 and B equals 2, and then calculated C equals A plus B. Now in this case, here I'm referring to my screen at line 3, C will be assigned the integer value of 3. Now, if after calculating C as the sum of A and B, if I then assign A a new value equal to 2, C does not change automatically. In that this calculation, this value that's been derived from a set of arithmetic operations on previously declared variables is not automatically updated when constituent data that makes up the operation changes. There are particularities about this for more complicated data types, but in the case of operations on scalar data types like floats and spools, if a value has been assigned to a variable that's a result of some operations on previous variables, the value of that variable does not update when the constituent data that made up its operation result changes. So in this case, at line 4, when I reassign A equals 2 and I print C, I will find that C is still equal to 1 plus 2. Of course, I can redo the calculation to update the value of C, but the update does not occur automatically. Now, the other interesting sort of primitive built-in data type is the string. And the string is a sequence of characters. Those characters can be numbers, they can be letters, but they are declared using a set of either single or double quotation marks. Say I want to declare a string, and the string is a message to all of you that says hello. I can do so in a pair of single quotation marks and then just type hello. Now, our strings can contain both letters and numbers. They're just all understood as characters in a string. And so I can say for some string B, with spaces and everything, the date is 8/1. And that is all a string. And I could, again, put that in sets of single or double quotes. I can have spaces, I can have numbers, and both of these are the same data type. They have different values, but they have the same data type, and the type is a string. Now, strings have their own operators defined on them. And in the case of joining strings, say I would like to take my first two strings that says hello and then states the date. I can join those into a third string by just adding them. Say C equals A plus B. And this is to say that the string C is equal to A with B added to the end of it. Fine, when I print C, I get my A string, hello, my B string, the date, and then my C string is both A and B without any spaces in between. And this operation can be done to an arbitrary number of occurrences of addition. So in this case, if I say wanted to put a space in between A and B when making my message, I can actually just do so right in line by doing A plus and then a string with just a space in it, and then adding B. A, which is hello, plus a space, plus B, which is the date. And now when I print that, I get a message that doesn't look so silly. And the strings also have all sorts of other operators defined on them. For example, if I multiply a string by an integer, that's what I've done here, A plus a space plus B times 3. And then I print that, I actually find that I get 3 repetitions of the string that I multiplied by 3. This is true for a couple of other data types, but here's sort of your first look at having operators assigned for different data types, particular to the data type, that may or may not be what you expect. Multiplying by 3 for a string results in a repetition of that string by the number of integers that you multiplied by. Now we've done a lot of print already. So the print function will take a string and print it to a terminal, whether it's in Jupyter Notebooks or in my case, just in my IDE. Got an integrated terminal here. And that's how I've been printing data in my case. And print understands a lot of data types, but not all data types. In the case of integers, floats, bools, and strings, print automatically understands that when given, say, an int or a float, it understands to first convert it to a string and then print the string to the terminal. That's actually what occurs when I say print 0. And I run that and I get a 0. 0 is not actually being printed per se, not the int, but actually a string of the int. And print knows how to do this for lots of types, but not all. Later today, towards the end of the day, we'll go through how to actually define that operation on data types that we design ourselves. But what's true is that, say, print when passed 0 is the same as casting 0 to a string. And string, the casting function is str. So int was for integers, bool was for booleans, float for real numbers, and then lastly str for string. And you can do this for assignment as well. So you can do C equals str of 0. That will do the same here. Do just a bunch of zeros, still get a 0 for the string. Whereas if I were to say do D equals these, but inside of the quotation marks, there's a difference. A bunch of zeros in the case of Python, just a bunch of zeros all in a row is the same as an int of 0, whereas putting a bunch of zeros in a set of quotation marks is a string of all of the zeros that are entered in the set of quotation marks. You can see that difference shown here. All right, let's do a quick poll, make sure everyone is with us so far. Just give everyone a second to respond to that. Make sure we haven't lost anyone so far. Main takeaways here being that we have our ints, our floats, our bools, and our strings. We can convert data from one of those types to another with rules that are particular to the conversion or the cast. And each of those types has operators defined for them, like using the addition symbol, the multiplier symbol, and they can have different meanings depending on the type that's being operated on. Those are the takeaways.
Excuse me, could you please tell a little bit about the shortcuts that you use for selecting the text in a fast way, you know, like you're jumping between the, like selecting them, I think using the shortcuts, specific parts inside the quotation.
I
mean the keyboard shortcuts, I mean.
Keyboard shortcuts for, like, say, executing code in Jupyter Notebook?
No, in the PyCharm, for example, you select, like, I think you press Shift and use the arrows to select them, then these kinds of shortcuts.
Oh, or some of it's AI based.
Like that, so.
Yeah, so some of this has to do with the AI being trained to my coding behavior. But yeah, for say executing a script in PyCharm is Control-Shift-F10 on Windows. These other things, you know, all the suggested code, yeah, like that. That's a combination of just built-in configurations for PyCharm for the language, and then studying me. But those mostly come up automatically. All right, so let's, I think we're good. So let's continue on. If you're a little bit lost or this is kind of whirling around in your head, don't worry so much about it. We'll get a lot of practice on this today. But let's continue. So another type of operation that we can do is we can say compare data, the result of which being a bool. We can say, is something, say, greater than something else? Are two pieces of data equal? Are they not equal? So on and so forth. And this looks like something you can see here on the right, or doing some very simple tests that I'm just going to make up on the left. So if we have our a equals 1, our simple integers, a equals 1 and b equals 2, we can ask, is a equal to b? And assign the result of that question to a variable. In this case, we'll call it c. We'll say c is equal to the result of testing, is a equal to b? And that operation is a double equal sign. A equals B is the test, is A equal to B? And we can assign the result of that test to a variable, again, calling it C. And when I print C, I find that C is equal to false. A is not equal to B. And when I change A equal to, say, 2, then I find that the test is true. Now, reverting and saying A is equal to 1 and B is equal to 2, we have lots of other operators like greater than or equal to. These are all using the comparison operators that one would expect. Maybe the most peculiar one is, in this case, the test for inequality. So if we have the test for equality being the double equal sign, then the test for inequality being the negative or the negation of is exclamation mark equals. So A exclamation mark equals B is the test, is A not equal to B? And now I'll find that when A is equal to 1 and B is equal to 2, I will get in the test for inequality my result C equal to true. So you can do this for different types of data in comparisons with varying mileage. So for some data types, the comparison to other data types is not defined. Much of this you can see here, I've tested on the test for equality for an integer and a float. And I get that the result is false. When I test A equals int of 2 and B is equal to the float 2.0 and I test for equality, I find that that actually returns that it's true. So Python understands a comparison of ints and floats under certain conditions. And again, different data types have comparison operators defined on them with respect to other types of data, most to do with how data is converted during a typecast. So mileage varies, very particular to the types of data that you're working with. This is one of those times where when in doubt, check Google. Now, there was one data type that we've kind of neglected a little bit, and that's a special data type, which in Python is called the none type. And the none type, for anyone who has worked in, say, like C++, none is the Python equivalent to null, which is a special value that roughly equals, or is roughly interpreted as nothing. And the abstraction and philosophy of this, I would like to not get into so much today, but suffice it to say that the none type has exactly one possible value, and it can be assigned to any variable, and the value is a reserved word, none, with a capital N. C is equal to none. And this special value can be compared to any other data type that's in memory. And one can always ask something like, if I say that C is equal to none, I can ask, is A equal to C? is A, the int 2, equal to none? And the result is false. Now I can say also A equals none and C equals none, and then test for equality, and I find that that's true. These are unique variables, both of which have been assigned the same value, and the value is the none type. And there's a special test for the none type, one that we've not covered yet. And the test looks like this. If I want to ask, is a variable equal to the none type? So without regard for what the type the data might be, I can simply ask, is a variable the none value? Or is it equal to the none value? And I can do that by saying, say in this example, D equals the test, C is none. So the operation test for a variable being equal to none, irrespective of its type, C is none. And the test for inequality, intuitively, is the expression is not none. The test to see if C is not equal to the none value is the expression C is not none. And I find that in this case, I assigned C equal to none, and then tested C is not none, I get a resulting value of false.
Does equal work? I think it does.
Yes.
Or exclamation equal.
Yeah, so these operations are defined, the equals and the exclamation equals. But you'll note that my IDE at least will show a warning, and that this is not a recommended expression. So you can do either. Most typically none is used for working with more complex types of data, in which case one can ask, has a particular type or has a particular value of some complex type been assigned to my variable? The options being that it either has, or my variable is assigned the none value, in which case the test is according to C is none. This question is more about the IDE and not about the language stuff. It's to do with the language. There are some expressions that are supported that are not recommended. And so you may find that you aren't getting some of the little warnings in Jupyter in your notebook that I'm getting in my IDE. And that's because PyCharm will tell me about when I'm doing something that's not recommended. Just like PyCharm will also tell me when I'm doing something that's illegal. When I do something that violates a syntax rule, I'll get a warning for an error. This can also be configured to tell you when you're doing something that technically Python will execute, but most people will frown upon if they see it. And that can be for various reasons, most of which are unimportant to us. In general, I try to stick to the recommended syntax. But yes, as Juliana points out, Python is very liberal in what it will execute because it's what's called an interpreted language. But because Python is so flexible with what it will execute, there tends to be a lot of recommendations about how you write your code. When it can do nearly everything, it's important to try to focus all of the creativity towards something that's comprehensible to others and to yourself, your future self. All right, let's continue on. Now we're gonna do, if I remember correctly, this is the last bit for our first module today before a quick exercise, and then we can take a break and stretch our legs. And sorry, I'm gonna get more and more hoarse as the day goes on. Forgive me. I'm gonna try to keep drinking water and hopefully I don't sound like a frog by the end of the day. So the last thing I think that we're going to do for this first module is we're going to do what we talked about a little bit with an excellent question that was asked earlier about why does Python sometimes fail when I put spaces before one of my expressions? And we talked about that Python cares about the spacing before your lines because it uses that to determine some of the flow and the logic of your software. And what I mean by that is that in Python and in other programming languages, one of the most useful things that you can do with software that you develop is to do what's called branching. And that is to design your software to make decisions and execute things based on those decisions. We've done, for example, the comparison operators. We had our simple, silly integer example of saying a equals 1 and b equals 2, and then test is a equal to b. Now, what's important is that based on those types of tests, like a test for equality or inequality, we can tell Python to execute certain blocks of code based on conditions that we express. Based on our conditional tests, we can execute certain lines of code, and that's called branching. And in this first example that you can see here on the right, we can do what are called if statements or if blocks, depending on who you ask. And they look like what's shown here. The basic structure looking something like this. This is true for all if statements. You can initiate or designate a block of code that is only to be executed under certain conditions using the template like what's shown here, where condition is the outcome of some test. In a very simple example, we go back to our a equals 1 and b equals 2. Here we'll say for c, c is the result of the test of whether or not a is equal to b. So c equals the result of the test for equality of a and b. Now c here is a bool, and bools can be used to designate or specify the conditions of a branch in our control flow. And I can do that like this. If I say if C, my bool C, if C colon. And then if you're following along, I'm going to return, and you'll notice that my IDE automatically adds a tab. And it does this because everything that follows in this block that is tabbed will all be considered as part of this branch that will only be executed if C is true. In this case, I'm just going to do something very simple. I'm going to say that if my test result C is equal to true, I'm just going to print the string that says true. Now, when I run this, A equals to 1, B equals 2, C is the result of the test for inequality, And now I'm only going to print true if my test for equality is equal to true. And when I execute this with A equals 1 and B equals 2, I get nothing printed. Now, if I change B equal to 1, which is what A is also equal to, and then I test for equality, now C will come back as being true. And when C is true and C is used as my condition, and I execute this, I find that now my software, my program will print true, and that is because the condition for this block of code was true. Now this is applicable for all of the comparison operators that we reviewed, as well as the tests for the none value. So if C is not none, so on and so forth. You can do these conditional evaluations inline in this if block. So instead of saying that if C, then do my code block, instead I can just write into this conditional statement, if A is equal to B, print true. And I find when they're not equal that my software prints nothing. When I make them equal, it prints true. Now, to continue on with that, it's also then possible to construct additional branches for our logic. The two other options, the first being to test for another condition on the condition that the preceding condition failed. Meaning, if the test A equals B fails, if I would like to test another condition, I can do that by starting another conditional statement, which is elif, E-L-I-F, which is a combination of else if, something like that. Elif, E-L-I-F, and a colon, and then return and indent, one tab. And elif also needs some sort of condition. And say, in this case, elif A, say, is less than B. So if A is equal to B, then do something. And if that's not true, then test is A less than B. And then return with a tab. And then I'm just going to print the operator, my less than symbol. Now let's try that. A is equal to 1 and B is equal to 2. My first branch did not evaluate because my condition A is equal to B was false. And then since that condition was false, then my next condition described in elif is then tested as A less than B. And in this case it was. And so this block executed. Now, the very last aspect of this is to specify a sort of last resort. That if all of my tests, because there are, you can define these infinitely, A less than 2 times B, so on and so forth. You can do as many elifs as you'd like. But then lastly, it's also possible to describe the sort of last branch that occurs if nothing else occurs. If all of my if statements evaluate to false, but I would like to have something that executes instead. I can specify that using else. And else takes no conditions. It's just else and a colon, return, and then tab. And that's it. So now I find testing for A is equal to B, or A is less than B, else just print else, or whatever nonsense you'd like. And in this case, let's say A and B are both equal to 2. When we run this, we get true. That was from here. A is equal to 1, B is equal to 2. I get my less than operator. That was printed from here because this was true. Now when I say A is equal to 3 and B is equal to 2, I get a printed else exclamation. That was here. And that was because A was not equal to B, and also A was not less than B. And that's control flow, at least using if statements.
TJ?
Yeah.
Show an example of more than one indented statement.
Mhm.
And then a statement that's not indented that actually shows that you've ended that control structure.
Sure. So it's possible to nest these structures. So within, say, a branch here, I can then also start another one and say,
Well, do the simpler one. So print true, print 47, A equals 96. They're all in the same indentation level. They're all executed with that thing. You don't necessarily need another layer of indentation, right? The whole thing about the space indentation is you can have as many lines indented as you want, and they're all part of that same code block, and you do as much as you desire to do there. And the whole thing ends the first time you get an unindented line that's not a clause on the if.
yeah. So then to get out of the block and start back in the main branch of a code, just go back to no indentation and say something like that. So each of these is executed conditionally based on conditions. And then once we're done with this set of control logic, then we can just remove the indentation or go back to the original level of indentation at which we were operating before this branching. And then continue on as we were. And that's true for nested blocks as well. So you can do things like testing for A being greater than 2, but only under the condition that A is equal to B, versus if A is greater than 2, but only under the condition that A is less than B. And then once I've done my nested logic, then going back to the level of indentation of this block, and then continuing on. So maybe you get a stronger sense now of why putting spaces before lines of code can potentially throw some errors depending on how your code is being parsed. All right, and then probably reserve this exercise for our break since we've kind of gone through most of this and I really don't want to get behind today. So I'm going to leave this up. We're coming up on a 15-minute break. We've got a module questionnaire running, if everyone could fill that out with brutal honesty. It would be very helpful for improving this content and these exercises and so on and so forth. So please, we appreciate the feedback. All right. James, do you have any closing commentary before we break for 15 minutes? Let everyone stretch their legs and all of that. Let me get some more water.
No, we'll be fine. Thank you. If there are any questions, please put them in the chat. We will try to help out with questions during the break. Otherwise, we'll see you back in 15 minutes. And please do fill out the questionnaire so we can adjust our lecture speed and content as we go forward.
All right. Well, I don't see any questions popping up. So let's break for 15. Of course, if you have any questions and you're typing it as I'm running off, just bring them up when we get back. We have all day. So yeah, let's take 15 and let's meet back at 12:15 p.m. Eastern. So see you on 15.
That's a lot better.
Yeah, I was looking to see if I can also, yeah, okay.
And that looks much, much better. The problem is, however big it is on your screen, my screen is smaller, plus on my screen, if I have it embedded in the Zoom window, it makes it even smaller still.
Yeah, I think being able to see this much at a time should be okay.
Yeah, no, this is much better. It's much, much better. Are your slides up someplace?
No, I've not uploaded them. I have the link. I'll upload all 4 modules once we finish today.
Okay. No problem.
All right, so it's 12:15. Maybe give everyone the rest of the minute to get back so we can reconvene. Don't want to delay for too long because we got a little behind on that last module, which is fine. This is the module that probably covers the most as far as minutia. So we're going to catch up a little bit, finish out the content for that module, and then get into module 2 very shortly thereafter. All right, so let's bring it back. It's 12:16 Eastern. Left an exercise up for those of you who wanted to get a little extra practice in on the break. This was just choosing a number, checking to see if it's even or if it's odd, and then responding accordingly. So in this case, to check for if a number is even is to check and see if the remainder of that number divided by 2 is equal to 0, in which case we can put that as a condition in a branch and print even if our condition is true. And if the condition is false, then we can have an else statement and print that it's odd. And then there was a little extra credit as well. responding to if a number is divisible by 4. Again, the remainder being equal to 0, in which case we'll print that message as well. And then the second bit of extra work was to actually specify a second number and check to see if the first number here called num is divisible by the second number here called check, and then printing messages accordingly. So when I define num is equal to 3 and check is equal to 4, and then I look at my outcomes, I see that num is odd, and I'm printing not by check when my first number num is not divisible by my second number check. So if you did these exercises on the break, maybe your code looks something like the one I wrote up here. All right, so I'm gonna clear my script. Let's finish out the content for module 1, and that is progressing more into capabilities concerning control flow in our software. So we've done the if-else statements, defining code that is only executed upon evaluation of certain conditions. Another capability that we have in Python is to specify that a particular block of code is repeatedly evaluated according to a condition as well. So we can use a keyword called while and say that while some condition is true, a particular branch of code should be executed repeatedly, where after every execution of our code, the condition of our while block is evaluated again. And that while block will continue to be evaluated over and over and over until the condition evaluates to false. So I can say something like this. Say I have some integer a equals 1, and I can say while a is less than 5, colon, just like with starting an if branch, and then say while a is less than 5, anything I type in here is going to be executed repeatedly until a is no longer less than 5, and I'll say a is equal to a plus 1. So the value of a is increased by a value of 1 at every evaluation of this branch. The shorthand way of typing this is a plus equals. Those of you who aren't familiar can also create comments in your code using the pound. So everything followed by this line, you'll see that in my IDE, this is grayed out. So this is a comment. And these two are the same. A equals a plus 1 or a plus equals 1. Those are the same thing. And now at every iteration of this block, the value of a is going to be increased by 1, and this will continue until a is no longer less than 5. And now we get out of this branch in the same way as with our if blocks. So we just return and go back to our original level of indentation, which is 0. And then let's just print a. So a is equal to 1 while a is less than 5. Increase the value of a by a value of 1, and then print a. And when I execute that, I find that the final value of a is equal to 5. Now we can see this in action by going back into this branch and say, let's do another print statement that says a string inside colon, and then again, we can print as many things as we like inside one print statement. So we can do inside colon, and then do a comma, and then just print A. And when we execute this, we see something like that. So started at 1, went into our branch, increased A by 1, and then printed A, and we got inside 2. After that execution, the condition is then tested again, is A less than 5? Well, that was true, and so we do it again, and so on and so forth until our condition is no longer true. And then the code continues on. Now, there's a faster, or not faster, a more abbreviated way of doing this with another set of Python functionality, which uses the keyword for. And for does a lot like what the while branches do, except that for can be much more specific as to what to actually iterate over. So in this case, when we instead start by saying for, we can declare some new variable. In this example, the variable's name is n. And say that our variable is going to iterate over a set of numbers, and we can generate this set of numbers using the function range. This is built in to Python. And when we say range of 5, range will return every integer starting at 0 up to but not equal to 5. So when we say for in range of 5 and then a colon, this branch of code that we specify in here will execute for n is equal to 0, then n is equal to 1, equal to 2, so on and so forth, until n is equal to 5. And when n equals 5, the code will return back to the software in the preceding level of indentation. So in this case, we can do something like for in range of 5 and just print n. Now we've essentially done the same thing as what we had done before of say if we had done a is equal to 0 and while a is less than 5, print a, and then a equals a plus 1. This will print 0, 1, 2, 3, 4, and then when testing for here, we tried to do a is equal to 5. The evaluation returns false, and this progresses into the next lines of code. Done the same thing here. Now this is a very limited example of a much broader set of functionality concerning for and using for to iterate over things. But we're going to reserve that for a little bit later mostly. But in general, this is how you can do iterations in just one line of code over some set of integers. Now range has some additional functionality. So when we here pass just a value of 5 to range, as I said, the default behavior is to iterate starting at 0. Do n equals 0, n equals 1, equals 2, all the way up to, but not equal to the value that was passed to range. Now, if we specify 3 arguments to range instead of 1, we can specify the first value in the iteration, and that here is denoted as start. So when we only pass 1 argument, start is equal to 0. But when we pass 3 arguments, we can first start by specifying a starting value of our iterator. This is what n is called. The starting value, if we say pass first the argument 1 for start, n will begin by equaling 1. And then we can specify our stopping value of 5. So in this case, when we pass range of the arguments 1 and 5, this will iterate from 1, beginning at 1, through every integer up to but not equal to 5. So when we run this, now I see I only get 1, 2, 3, and 4, but not 0. Or 2 and 5, get 2, 3, and 4. Now the third scenario, this is the one that's actually listed here, is specifying the step in an iteration. So when we don't specify a third argument, then our iterator is incremented by a step equal to 1. At every iteration, n is increased by a value of 1, but we can change the integer by which our iterator is increased. And in this case, we can say specify a value of 2, in which case this will begin at 1, and it'll increase at each successive evaluation of our branch by a value of 2 until n would equal 5, in which case it stops. And so in this case, passing 1, 5, and 2 for start, stop, and step, n will equal 1 and then 3. And of course, other stuff in our branch. And you can test this out as much as you'd like. Okay, and so I'd like to just, get, James, can we do a check-in with everyone and see, make sure everyone is keeping up while we work through this example together real quick? All right, so real quick, I think we have one more person working. Let's just do this together very quickly. So we have 2 positive numbers, say A and B. Let's do A equals 100 and B equals 200. I want to sum every odd integer from A to B inclusively. And so we can do this a number of ways. Let's just do a very simple case. So let's do, actually, no, let's not do a simple case. Let's practice our 4s. So let's say we're going to declare a variable called result. And result is where we're going to store the summation that we're going to do over the range from A to B inclusive. And so let's just start by initializing that equal to 0. And now let's say in a for loop, let's say for in range. And let's use 2 arguments. Let's specify iterating from a starting value of A, being the beginning of our interval, and let's do up to our second value B, while handling that range will only iterate up to, but not equal to, our stopping value. In which case, to also iterate up to the value of B, we have to pass B plus 1. So for will iterate up to, but not equal to B plus 1, in which case the last value that will be iterated over will be B. And let's do a colon. Let's go into this branch, and we only want to do odd integers, in which case let's do a test to see if n is odd, and we can do that by saying if n, and let's find the remainder of n divided by 2, and if n is odd, then the remainder will not be 0. So if the remainder of 2, or n divided by 2, is not equal to 0, and let's add a colon, and in this second level of indentation, we'll add n to our result. Result equals result plus n, or in some shorthand, just result plus equals n. And let's get out of our if branch, and let's get out of our for branch. So we're going to go all the way back down to no indentation, and let's return a line, and let's just print our result. So for A equals 100, B equals 200, should find that result equals 7,500. So again, there are quite a few ways to do that. Could have specified a different step, could have specified different starting conditions, and moved the test for whether or not n is odd. Lots of different ways to do it. What matters is that the result is correct. So again, these slides will be made public to everyone after our sessions are over for today. So if you want to revisit this, by all means. Now, something interesting that we really don't get into all that much in CompuCell, but it's certainly possible, is how to actually terminate a branch that's being iterated over preemptively, something like an interrupt. So if, for example, I am doing some sort of while loop, beginning with A equals 0, and when I say while A is less than 10, and I'm going to do some stuff, including increasing A by a value of 1 at every iteration. Now say for whatever reason, I want to actually break out of this branch early, as in before this condition is no longer true. I can do that using what's called the break keyword. Break will get out of a branch and return one level up in some hierarchy of control flow. So if, for example, I say I declare another variable that says, I'll just make it a Boolean and say B equals true, just for fun. Now let's say that in our while loop, if B is true, and then if A is, say, greater than 5, then break. Or as a way to join evaluations of comparison operators, we can use what's called the AND keyword. And we can do that by just doing this. If B and A is greater than 5. This evaluation is a combination of both testing is B true and also is A greater than 5. Boolean operators also define OR in exactly the way that you would expect. If B is true or if A is greater than 5. We'll do, in this case, if B is true and if A is greater than 5, then we'll break. And let's print A and see what we get. So when B is false, this never gets evaluated. And we should get, yeah, A is equal to 1, 2, 3, 4, 5, so on and so forth. Now, when we set B equal to true, this will always return true. And so when A is greater than 5, then see now, as we print A, once A is greater than 5, the break occurs and we get out of our iterations. So here's a comparison of using those two. Each of them has their own uses. I'll leave this to everyone to sort of think about a little more as we progress through the week and in their own time and in their own practice. And so now we're going to switch over to what is officially Module 2. Wouldn't worry too much about time. We will certainly get through everything today. There's just a lot to get through in that first round with data types and all of that, so no problem. All right, so now we're actually, let's do a poll real quick and make sure, yeah, make sure everyone is all caught up. Because next we'll be getting into some new types, lots of new functionality, things that we use every day in CompuCell modeling for sure. There's the deleted code real quick for your reference. So I can leave that up for a few minutes. All right. So we got a few more said they need a little more time. Give it a couple more minutes. And then I'm going to move on to new types that are divisible. Our scalar types been indivisible. We can't break them up into, say, subunits of more data types or types of data. Now we're going to move on to sequences. So I'll give everyone another 30 seconds and then we'll get going. So let's talk about sequences. So I'm going to start to think about how we take collections of data of various types, say scalar types or more complicated, and organize them into collections, into groups, based on however we please. We want to design something like a container that has a set of data that we may be interested in. We're going to look at some different ways that we can conveniently store, organize, manipulate those sets of data in one-dimensional containers called sequences. So the common ones that we'll mostly work with, one of them we've already used, which is actually the string. So the string is actually not a scalar type. The string is actually a sequence of individual characters. In more complicated and more general examples, we have most typically lists and tuples. We'll go through both of those today. What is a list? What is a tuple? To just start, I've got an example here for these two sequence types. We want to say take a set of integers and put them in what's called a list. We just write out all of the different elements that we'd like in our list, separated by commas, and then enclosed in a pair of brackets. Now what that actually constructs we'll go through, but to start, you can build a list. My list equals, and then say 1, 2, 3. Print the type of my list, and let's see, Python tells me that my list is a list. And for tuples, it's quite similar. Tuples are specified in the same way, except they're enclosed in parentheses. I print the type of the variable my tuple specified like that, I get a tuple. Now, like the types that we've already worked with, there are specific operations that are defined according to these different types of sequences. We've already seen this example of when we add two strings. We found that two strings, when added together, just end up getting merged together, where one gets added on to the end of another. There are additional methods that are defined that are specific to sequences. The first of which is to just say get what's called the length of a sequence, in that the length of any sequence is the number of elements in that sequence. In the case of all of the sequences, the function for the length of a sequence is just len. And when I pass any sequence to the function len, it will tell me how many elements are in it. I see there's a question about the difference between tuples and lists. We will get into that. And there are some very specific ones. So it's a great question. In some ways, they're very similar. In other ways, they are quite different. Both of which, though, are one-dimensional. And so when I say declare some variable my list equals the integers 1, 2, and 3 separated by commas and in brackets, and then I print the function len of my list. So we're going to calculate the length of my list. Just call it my len, and then print it. I get 3. That's the number of elements in my list. Now I'll note here that it's possible to also define empty lists. So a list that doesn't necessarily have anything in it, And that can be done by just having an empty bracket or set of brackets. So if my list equals, and then just a set of brackets, that's perfectly valid. And when I calculate the length of my empty list, I get a length equal to 0. Now that's also applicable for both tuples and strings. So in the case of strings, when I say calculate the length of some string, get a value of 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, including the space. Now, there are comparison operators that are also defined for certain sequences. And those are particular by the type of sequence. We'll go through those a little bit more here in a little bit, but more notions of having the same, say, specification of an operator, but actually meaning something different depending on the type. In the case of strings, for len, for example, that calculates the number of characters in a string. For lists and tuples, it's the number of elements. Now, all of the sequences have a set of operators to do what's called slicing. And slicing is a way of getting particular elements in a sequence. Now, in general, we can access individual elements of a sequence by using what's called indexing. So for example, if we create some list that's my list of integers 1, 2, and 3, I want to get a particular element from a list. I can access it by index as follows. I want to get, say, the first element of my list. I can index to it using a bracket on the name of my list. So my list and a bracket, and then the index of the element that I would like to have or access, where the first element has an index of 0. So in this case, for this example, my list has values of 1, 2, and 3. And to get the value of 1 would be an index of 0. To get the value of 2 would be an index of 1. To get a value of 3, it's index of 2. And slicing is a way of doing this accessing of elements within a sequence, but more than one at a time. So something like a subset. And this looks like this. So let's switch over to working with strings. Strings are also sequences. So let's have some string, we'll just call it S, and just equals a bunch of nonsense. B, C, D, E, F, G, H. Just going to list some of the first letters of the alphabet, and we can do these slicing operations to get certain subsets or like groups of elements within our sequence using the following operations. So when we were getting individual elements, we would say my car equals and then S of 0. S of 0 gets the very first element of this sequence. In this case is A. Now, like when using the range function, can do something similar, but inside this indexing operation, where we can specify the first index of a slice. In this case, I'm going to start with 3. And I want to get every element up to an index of 6. So 3 is my starting value, and every index integer-wise up to but not equal to 6. So here I get index of 3, 4, and 5, but not 6. And like when we worked with the range function, we can also specify the amount that this index iteration is increased by at every iteration, where the default value is equal to 1. So without specifying a third argument here, this will do 3, 4, and 5. Whereas if we say from 3 to 6, increasing at every iteration by a value of 2, this will do 3, and then 5, and then stop. So index 0, 1, 2, 3, then increase by 2, 5, and when increasing by 2 takes me past my stopping value, and so the slice stops. Now there are a couple of sort of shorthand operations defined here. So if, for example, I just enter nothing in between these colon separators, this is the same as copying the values of S into a new variable, my car. And if one would like to, say, iterate backwards, beginning with the end, and then moving all the way to the beginning, one can specify nothing between, or nothing as the first two operators, and then for the step, the third argument, just enter a value of -1. You'll see this is now printing my original string backwards. See, the question is 2 colons or 1 the same thing? The answer is yes. So to make a copy of a sequence, whether it be a string, a list, or a tuple, can either just enter 1 colon or 2. So this is to say, when entering 1 colon or 2, this is to say use the default values of each of these arguments. And in this case, the default values are 0 for start, a stop equaling the last character of the sequence index plus 1, and then a step equal to 1. So those can be used interchangeably. And then when iterating in the negative direction, one can also specify starting and stopping conditions, excuse me, where the starting condition is greater than the stopping condition, which is necessary because I'm iterating in the negative direction, as specified by negative step value. So this will start at an index equal to 4, 0, 1, 2, 3, 4, and then decrease by 2 steps, and then try decreasing another 2 steps, but that is equal to our less than our stopping condition, and so we get EC. So these operations are also true for working with other sequences. I would say it may be a little strange for some, this notion of, say, indexing negatively. So in general, Python will wrap a negative index back into a sequence starting at the end or the length index of a sequence. So if, say, doing s equals 0, s with an index of 0, index of 1, s index 2, this is doing A, B, and C. But then one can also do the exact same thing going in the negative direction, s with an index of -1, -2, -3. -1 will be the last element in the sequence. The index of -2 will be the element before that, -3, the one before that, and so on and so forth. I'm gonna skip this example and leave this to everyone. I'll provide some code for what actually does this. I'd like to continue on for now so we don't get behind again. So this will be made available after today's lecture, and of course I'll be available to answer any questions for how to get through this. But I'd like to move on, check in with everyone, make sure we're all up to speed. All right, give it another minute, see a few people need a little bit more time. All right, let's continue. This is a good exercise. I think we can do this one probably pretty quickly. So let's do this one together. So in this exercise, we're going to start with a string. We can work with whatever word you like. We could just work with the first few letters of the alphabet. And the exercise is to create a new string that is the original string in reverse. So let's do this together. And let's do it like this. Let's practice our for loop. So let's do an iteration over the length of our original string, which in my case I've just called S. Let's say for in and range. So we'll have an iterator iterating over some range, and let's just say from 0 to the length of S. Remember, if we don't specify multiple arguments, then the starting value of our iterator will be 0, and it'll iterate up to, but not equal to, the length of S. And let's enter a colon. And now let's go back up and let's declare a new string, and we'll call it new S, and let's just start by creating an empty string And the creative way that we're going to do this, we're going to practice a few operations. Let's do at every iteration, we're going to add to new S. Remember, if we take two strings and add them, it'll join both strings together. Let's say new S equals new S plus, and then something from S, our original string. And the thing that we'd like to get is beginning at the end of our original string. Get H, then get G, in my case, get F, then E, so on and so forth. We're going to do that using negative indexing. Now recall that an index of -1 refers to the last element of a sequence, and then the one before that, and so on and so forth. And so what we can do is, beginning at -1, for n beginning at 0, we can just do -1 minus n. So n equals 0, this will be -1. When n equals 1, this will be equal to -2, then -3, so on and so forth. And this is just being added over and over to our second variable, new S. So let's run that and let's print it at the end. And there you go. Now I see there's at least one comment in the chat about a one-line solution to this problem. Totally acceptable. And most often, not most often, I don't want to encourage any particular behavior, but very often briefer code can be better code. So lots of solutions to do this. Just a little bit of practice here with some of our content for today. So I'll have another version of this posted online as well for your reference. Let's go ahead and move on from that. Now again, these operations also work for generating lists. From lists, you can also print these slices directly. So for example, the list type has functionality built in to be able to print them directly. So you'll notice when you declare some list from the integers from 1 to 4 and then print it directly, we'll just get a string of the list elements printed directly. And it's also possible to say print slices of those lists as well, or of sequences in general. You can also do assignment. So it's possible to say assign to subsets within sequences or subsequences, however you want to think about it, using slicing as well. So if, for example, you'll notice here I have my variable myList. That's a list from 1 to 4, the integers from 1 to 4, and I'm just doing a slice to index the second and third elements. And you'll notice that then if I do something like myList, and then slicing from 1 to 3, I can actually declare that as a list, something like within a list. But it's not a list within a list. What it is using this slicing to create something like a temporary sequence consisting of all of the elements that I've accessed using my slicing operator, and then assigning to each of those values in that sequence the corresponding values in this list that I've declared here on the right-hand side of my assignment operator. So this is accessing elements 1 and 2, and then saying assign to those elements 1 and 2, assign the new values of, in this case, 5 and 6. We print all of this all at once. You see, I start with my initial list of the integers 1 through 4, doing some slicing just to get the first or the second and third elements, which are 2 and 3. And then by assignment, using the slicing operator, actually replacing the values of the second and third elements of the sequence and setting them to 5 and 6. Just as a quick note, we worked with the range function in the previous module. It's also possible to use the range function to generate lists quickly. In this case, if I wanted to instead generate this list of 1 through 4 using range, I could have also done something like passing to the range function the starting and stopping arguments of 1 through 5 that iterates from 1 up to but not equal to 5, and then taking that and passing it to the list constructor. The list constructor meaning the name of lists as a Python type is just list. And when I pass the return value from range to list, it will create a list consisting of all of the elements that were returned by range. In this case, 1 through 4. Or 1 through 8, if I change the arguments from 1 to 9. So just as a quick aside there. So an interesting distinction between our strings and lists that we've worked with so far, and we'll find a distinction like this for tuples as well, is that elements of string sequences can't be changed. When you declare a string and then try to change, say, one of the characters in a string using indexing or slicing, you'll find that you'll get some kind of error. And that is because the string is called immutable, in that once it's been declared, the elements that it consists of cannot be changed. Say S equals ASFD and then S of 1. So indexing to access the character S in ASDF and try to change that to B, and I get an error. Specifically a type error that says that the string does not support item assignment. Now if I try to do the same with the list, obviously, as we've seen, this will work. My list and try to index to the second value and change it to 4. No problem, because lists are changeable. Their elements can be changed, or they are what's called mutable. Whereas strings and also tuples, which we haven't really worked with yet, tuples are both immutable in that once a string or a tuple has been declared and the values have been assigned, the underlying elements of those sequences cannot be changed. You can create a new variable with new data, but you cannot assign new values to individual sequences that are immutable. Now, I've neglected tuples mostly because most of the operations on tuples, which again were declared using parentheses instead of brackets like in lists, most of the functionality of tuples is the same as lists. Most of the operations that we see will be the same for lists and tuples. The only major difference being that tuples are an immutable type of, or immutable version of lists or vice versa, in that you cannot modify underlying elements of tuples. One cool thing about all of the sequences list tuples and strings in this case is that they can be very easily iterated over in for loops. So up until now, we've been doing things like for in range of 5, and this will go from 0 to 4, every integer. Now, if I have a list or a tuple or a string, let's do a string. Say my str equals ASDF. Now, what I can do is actually create an iterator in a for loop that instead of iterating over some range of integers, instead, I can actually iterate directly over every element of the sequence. In this case, for a string, I can say for, let's say, some iterator named s, for s in, and then just pass the name of the sequence. For s in my str, and then just print s. And you'll see here that this is iterating over every element of this sequence, the string that's been declared here. We can do the exact same for lists and tuples. So let's say my tuple equals, and as Jim pointed out in the chat, you can declare tuples with or without parentheses. I prefer and recommend the parentheses just to make things explicit and clear. Say my tuple equals 1, 3, and 5, and then say for t in my tuple. And just print t. You see that in this branch, every element of the sequence that I've passed is being accessed and is available to do whatever we please in this branch. I'm going to check in with everyone, make sure everyone is doing well. Make sure we haven't lost anyone yet. See, at least one person needs more time, so give this a second. All right. Let's continue. Got a couple of examples here included here for your reference and your review. Those will be available with the slides after today. There's a nice example here of how I think to make code more intuitive to work with. This is one of the most invaluable things about Python, in my opinion, is that it's very close to something like almost like how you would actually describe operations with, in common language. So you'll notice here, as I pointed out, that it's possible to construct an iterator to index over, say, all of the elements in a sequence. But one of the most powerful things about these just very basic sequence types is that then you can start to construct code that works directly with the elements and in, excuse me, in something like, a comprehensible way. So not actually going through and accessing each individual element of the underlying data, but instead iterating over the data in the sequence itself. Excuse me. Now, of course, it's important to point out here that for the sequences are order specific. So the order in which the data is input into the container or the sequence when constructing it is then the corresponding order by which it's organized when doing things like iterations over it. All right, so maybe give everyone a couple of minutes to kind of work through this. So this is an exercise of taking two strings, excuse me, taking two strings and printing all of the characters that can be found in both strings. And so this is possible by doing something as simple as what's shown here on the right. This is simply just taking, say, S1 equals some gibberish, and S2 another string equals some more gibberish, and just iterating over both strings. Say for I in S1, I will be iterating every element of my string S1, and then for J in S2, iterating over every element in the second string for every iteration over the elements of the first string. And then just ask, is I equal to J? This operation, this comparison is defined for strings. Are two strings the same? And if they are, just print it. Run this, and in my two gibberish strings, this will go through and tell me all of the characters that are in both S1 and S2. There's a good question in the chat from AJ about if elements in a tuple need to be numbers. We'll go through this here in a second. We can come back to this exercise. Yeah, AJ, excellent question. So one of the main differences between strings and the other two sequences is that both lists and tuples, well, you can try this experiment on your own along with me. Let's say my list equals, in every example we've done so far for either lists or tuples, my tuple, we've got just an empty list and an empty tuple. We've been doing things like a list consisting of integers. Can we also do, say, a list of strings? Or say a tuple of a float and a string and an integer. You see, when I run this, I get no errors, and that's because for both tuples and lists, the data contained by both of these sequences can be heterogeneous. It's possible to put not only whatever type you please into one of these sequences, but it's also possible to put whatever combination of types you want into one of these sequences. So this not only supports doing heterogeneous data with, say, combinations of strings, floats, ints. It's also possible to do that with other sequences, like shown here with the strings. It's also possible to do things like make lists of lists and so on and so forth, as well as more complex data types that you or someone else has designed. So tuples add, tuples and lists both add like strings. So we saw this in module 1. If we had 2 strings, then we added them, then the 2 strings that are being added would just be joined together, and that would be the result that's, in this case, being assigned to some new variable S3. S3 being S1 plus S2, where S1 and S2 are A and B, respectively. Same is true for tuples and for lists. So we can try this out. Say A is equal to a list of 1, 2, and 3.0. And B is equal to, I don't know, 2.0 and some string A. What is, say, the result of A plus B? You'll see here that for A and then B, here's the elements of B, and here are the elements of A. This is the result of adding 2 lists, is that the elements of one and the elements of another are added together, and that's the result of this operation. The same is true for tuples, and this can be very quickly converted into a test like that. But for tuples, just by replacing the brackets with parentheses, you see now got the same data, but instead of being in a list, it's in a tuple. We'll note here that the addition operator here, I feel strongly implies that there is also a corresponding minus or subtraction operator, something like removing elements B from elements A or something like that. You'll find that this is not the case, that for both lists and tuples, for the sequences, this subtraction operator is not defined for those sequence types. Of course, as we'll go over later today, you can design your own type of list that does support that operation. But the list, tuples, and strings that we'll work with that are built into Python do not support this. Now there's a bit of details here that I've more left in for your reference than really wanting to dive into today. But tuples have, for example, some interesting ways that they can be used to be able to, say, do substitutions or say switching values in pairs that have been passed for different operations. And in particular, what I wanted you to see here is how to declare something as a tuple as opposed to getting, say, a scalar value back with some syntax that you thought might have generated a tuple. So in general, I think it's clear that to say declare a list with one element, one can just take some value for an element and enclose it in a bracket. Now, when you try this for a tuple and just say, for example, my tuple equals 1 in parentheses, let's print the type of this variable that's created, and you'll notice here that when I just say parentheses 1 to try to create a tuple with one element that has the integer 1, I actually get back an int. So a tuple is not created by this. And now let's try this with also with my list. We can print the type of, and you see that this actually works for the list. So in the case of tuples, for creating tuples that have a single element, what's necessary is to also include comma. There's nothing trailing that comma except the remaining parenthesis of the parentheses. But this tells Python that this is a tuple and it has one element, as opposed to being an integer. Now you notice that the same is not true for creating an empty tuple. So if I put a comma in parentheses, I end up getting an error there. In that case, you can do something like actually using the name of the type, which is tuple, all lowercase, and empty parentheses. That creates an empty tuple. All right, I'd like to go back and how much time do we have? We're on until 1:45. All right, let's continue on and we'll come back to this exercise if we have time. Because I'd like to reserve a little bit of time on some of the operations that we have at our disposal that make lists and tuples and strings a lot more powerful and a lot more useful for everyday applications, in our case, in modeling cells. And we've seen this. Now, let's try this. So we had the case of adding two lists, and what we found was that we could combine two lists into a resulting list by just using the addition operator. So if I have some lists A and B, and I just put some random data into it, and I say C equals A plus B, that created a new list that was the combination of the data in both A and B. Now, lists in particular, they have additional methods defined on them to be able to do operations on the lists themselves. So for example, in this case, shown here, we want to do something like this addition operation, but instead just add the data from B to A, not while creating a new list, but actually just adding, or what's called appending, the list data of B into A. Instead, we can do something like using this method append on this list A, and we can do that as follows. So a list has methods that can be accessed and used by first typing a period after the name of our list. So if A is a list, I can use methods defined on that list by using a period. And you'll notice on my screen, I get a lot of functions that pop up to pick from. In this case, I'm going to use append. And when I say a.append, this is a function, and we can pass something to it. The thing we're going to pass is, say, the first element of B. And we would do that with B, and then use an index of 0. So A dot append, and then pass the first element of B. We find that when we print A after this operation, now A has the first element of B. And of course, what's passed into this append function is not reserved to data that's in lists, but can just be arbitrary data. So A dot append of 0 will add a 0 into the list here called A. Good question. How can we see the list of operations available for an object in Jupyter? Unless there's some upgrade that I know of or I've not heard of, I don't think you can. I don't work a lot with Jupyter notebooks, so James or Giuliano or Jim, please correct me if I'm wrong, but this functionality of generating these function suggestions is not something that Jupyter notebooks will do. Is that correct?
I think you should be able to do a dir on the function. I mean,
Yes.
dir on the object.
Yeah, so there's a way, there's a built-in way in Python to be able to see everything that's defined for a particular variable. This may be one of your best friends. I know it's one of James' favorite functions in Python, if not his favorite, and that is dir, as he suggested. So when you pass any variable to the function dir, and then print that, you find this list of names of all of the things defined for that variable. And most of them may look fairly incomprehensible, not familiar at all, but you'll notice that one of them in that list for my list variable was the name of the function append. And actually, the names of all of the things that were suggested that pop up in my IDE, those are all available by printing dir of A. So that's the fast and dirty way to get that information. Another excellent question in the chat, reading my mind, which is how do you append all the elements? Presumably all of the elements in a list that's been passed to something like an append function. And that actually takes us to our next slide, which is one of the next most commonly used functions defined for lists, which is called extend. And extend, yes, as Giuliano just answered in the chat, extend is like append, except extend will append everything passed to it from that's in a sequence. What I mean is, we say a dot extend and then pass the sequence, here the list, B, and then print A. We find that all of the elements of B have been appended to A.
DJ, show us what happens if you do A dot append B.
Excellent suggestion, Jim. And maybe this is a thought experiment to pose to everyone to think about for 10 seconds. If I do say A dot append, so append to A, but instead of passing an element of B, I pass B, the list, what goes into A? And as mentioned earlier, both lists and tuples support heterogeneous data, including other sequences. And so when I say A dot append and pass B, the list B gets added to the data of the list A. So a list within a list. Excellent suggestion, Jim. Thank you.
Are you going to cover VStack and HStack?
If we get to it a little bit later.
You might just mention that those are the standard tools for doing.
Okay. Excuse me. Now, there are a lot of operations that are defined for lists and tuples, and again, as kind of demonstrated by the number of suggested functions that pop up for in my IDE when doing operations on these lists. And so it's certainly not possible to go through all of these. We'll hit a point today where we'll sort of like highlight maybe our favorite or the most commonly used features of these different types like tuples and lists and strings. And then, that will almost certainly consist of a limited subset of all of the possible functionality that's defined for that type, or later for functions and modules and all sorts of complicated things. And so probably starting now, there'll just be the running assumption that what's described about these, in this case, these sequence types and for everything else, that what I'm telling you about is a very small fraction of what actually exists. And so in this case, we've talked a little bit about adding elements or appending elements to sequences. We can do the same for lists, not tuples, because tuples are immutable. But for lists, we can do things like remove specific elements. So if, for example, I have my list A that has an int 1 and a string A, so heterogeneous data that has a sequence in it. And I say A dot remove. If I pass, say, 1, the int 1, and then print A, I'll find that the element 1 is no longer in A. Remove removes the value passed to it from the list on which remove was called. Now, if we try to pass a value that's not in the list, we'll get an error. In this case, a value error. And in my case, I'm given an explicit message that what I passed is not in the list. That's nice. On the other hand, there's also a very commonly used method called pop. Pop is like value or remove, except that instead of removing an element by value, I'm going to remove it by index. We can do A bracket 0 to get 1 by the index 0. We can do A dot remove of 1 to remove 1 from A. Or we can use A dot pop and give the index of 0. And we find again that 1 has been removed. If we pass an index that's not defined for this list, meaning that the index is greater than or equal to the length of A, get what's called an index error. It says pop index out of range. Tried to pop an element that wasn't there. And then there's, of course, a built-in method that's not as commonly used for these types of operations, but there's a way to delete things directly in Python, not things as in your hard drive, but as in variables that have been stored in memory, and that's just called del. And in this case, when I say del a of 0, this is delete the first element of a. And yeah, now you see that the first element of a is automatically removed by deleting it. And if I say del a and then try to print it, you see a is not defined. It's not defined at line 5 because I deleted it altogether at line 4. Okay, there's a lot of operations defined here. And again, this is a question in the chat. Can you pop multiple elements? Multiple elements in the case of doing something like that, perhaps? Okay. Yeah, good question. So slicing operations like this are not defined for pop. And of course, it's possible to do something like slicing like this. Notice here, I've done a slicing operation to get both the first and second elements of A and then delete them. And I find that when I print A, it's empty. But for pop, no. Yeah, exactly. Good question. All right, I think we're coming up on lunchtime. There are a lot of, again, operations defined for all of these. So I'm actually inclined to leave it at that. And if anything, share the link to the Python library documentation to be able to quickly find where the documentation on all of these methods, which I have not done justice for. I mean, you can see there are lots of functions like reverse to reverse the order in memory and so on and so forth. I don't feel that it's particularly important for us to master a strong knowledge of all of the things that are defined for these types, but rather to have a strong sense of what can be done and a working knowledge of where to find the information on the details. So we've got a questionnaire going. I'm going to call it the end of this module, and again, make these slides available. There are a few exercises and some more details on some of the particularities of sequences. Again, very much a subset of the functionality that is well described in the Python documentation itself, which I'd be happy to help you sift through and look for information on. And then, of course, there's an exercise here that's included at the end of the slides. I will also provide the scripts, the solutions for all of these exercises, just something that how I designed all of my solutions for the exercises. Those will be available as well. So don't feel like we're missing out on content for the sake of making lunch.
TJ, if over lunch you could possibly post the slides, even if they're preliminary, to the student materials folder. I think there were several requests for that.
Yeah, I will post all 4. Everything that we have or will do today, I'll just post all of them.
Yeah, if you could do that during this break, that would be great. And then you can always edit them after you've revised the talk.
Yep, will do.
So I guess we'll see people back at 2:15.
Great.
Is that the plan?
Yeah, that sounds like a plan to me. So see you all, stretch your legs, and enjoy not hearing the sound of my voice for 30 minutes.
And please do fill out the poll if you can, so we can update the material as appropriate. Sorry, TJ. You
Yes.
there? You probably want to make me host again. Who's host now?
You are.
I think to be host twice. I don't know what happened. Okay. Sorry, I know you've got to get started. Let me leave and see if I can. Okay, I apologize for the Zoom error. I will, it seems to be working okay though, so please go ahead.
Okay. Would you like to maybe give people a couple of extra minutes to get back? Okay.
I'm sorry, it has me in, if for some reason it has me logged in twice. And I don't seem to be able to get rid of that ghost copy of myself.
It looks like the recording and the live stream are both still working.
No. I just don't want to have the sound be, I can't mute it. So if
We can't hear you, James. You're muted.
good, so that's fine.
Cool.
I just wanted to make sure that ghost, because I can't mute that ghost. I have no control over it. So.
Okay.
Never had that one happen before. Sorry, everybody. There's always something, right? Okay. Okay.
Hey,
Back to you.
TJ, I got a question about if someone had saved a file in Jupyter, where is it if they want to go back and recover it?
It should be, yeah, they should be able to open it in their, if they're working on NanoHub, then it should be accessible in their NanoHub drive. In the in the menu bar under File, you should be able to select Open.
Yeah, if you do that, I think the big question is if you do that, you get a list of folders. Bin, data, doc, examples, middleware, Rapture, source.
Yeah, and
Any idea which one it would have been stuck into?
it would have been in that root directory. is where it should be saved by default. So like the copy that I created at the beginning of the day.
Okay.
Yeah, that's stored in my root drive where bin and data and all those are.
I recommend using the save as or save a copy, and then you can select the folder.
All right, so I hope everyone had a good break. It was nice to be quiet for a second, I'll be honest. But I'm glad to be back. We're gonna spend the rest of our time working at a little bit of a higher level, doing what I think are some of the funner things about Python. We'll see how it goes. So of course, questions in the chat, raise a hand, let us know if moving too fast or any of that. Otherwise, I'm going to get my screen share going. And we're going to start back this afternoon, our time, working with functions. So earlier today, we were working with a couple of operations that I believe I sort of justified with the statement of "it works, just trust me." So we've been using, say, the print function. In our last module, we were working with len to calculate the length of sequences. So we've talked about and also worked with built-in functions. And somewhere there's a specification for what actually happens when those functions are called. Somewhere there's a script or a library that defines len and print and range. And what we're going to do now is work through the basics of how to write our own functions. So take little packets of something like procedures, something that you would do often, at various points, various branches of some code that you may be writing. You want to formalize and sort of package this set of procedures into a way that is then callable, just like how we've been calling range and print and len, and that's a function. So we're going to learn how to define functions. So functions are extremely useful for not only being able to compartmentalize and formalize typical sets of calculations or procedures in your software, it's also a really good way to be able to actually clean up your code. I mean, it doesn't take long for CompuCell models even to start reaching hundreds of lines of code if you're doing a lot of advanced modeling in Python. And so writing functions and later today writing your own data types, these are excellent ways to be able to formalize what you're doing in your your advanced models and your complicated scripts, make everything very easily debuggable, testable, and shareable. And so we're going to work through those details now. In the very least, a function definition has a couple of basic components. The first being a header. And the header, which is this first line here, first tells Python that you're declaring the definition of a function. And you do this I'm going to go ahead and move over and get some code going as well. To do this, notifying Python that you're describing a function by first using the keyword def. You notice in my IDE that def turns orange, much like none or and def. And in the header, the next thing that we specify is the name of our function. In this example here, this is writing a function called isEven. I'm going to write one called isOdd. Def is odd. That is the name of my function. Def is odd. And then the next component of our header is a specification of all the arguments that can be passed to our function. When we reviewed working with the range function, we found that we could pass one argument to iterate from 0 to some passed number, iterating over every integer. When we passed 2 arguments, we could specify both the beginning and the end of the range over which we were iterating. And when we passed 3 arguments, the third argument we could use to specify by what step we do our iterations. Now, the function definitions in these headers specifies the arguments that can be passed. In our case, we're going to keep it simple and just say we have a set of arguments that can be passed to our function and not worry so much about optional features and arguments. And we're just going to say that if our function can take an argument, the argument being passed to our function from the outside world, we start some parentheses, and we just give a name to the argument that can be passed according to however we want to name it. And we're going to use that name to refer to what's passed when we work with the argument inside of our function. For example, if we want to calculate or develop a function that returns whether or not a passed value is odd, we could call the argument passed to our function I, and in all of the procedures that we perform inside of our function, we'll refer to whatever is passed to our function as I. And in a very simple case, in general, we want to return a bool that states whether or not something passed to our function is odd. And we can test this by saying the remainder of I divided by 2, is it or is it not equal to 0? If it's not, then I is odd. This is our test. If the remainder of I divided by 2 is not equal to 0, we'll call that result. So that's the result of our test for whether or not this variable I, whatever it is, test whether or not it is odd. Now you'll notice that the body, which is all of the code that actually defines what goes on inside the function, all of this is indented. And the function definition will continue no matter what we write until Python finds a line in the code with no indent. So there's nothing in particular that has to specify whether or not the body of a function has terminated, except it finds, as technically, 2 lines with no return or with no indentation. Now, a function like what we've been using would return something. We've been, say, doing for in range of something, or assigning the returned value of len to some variable that then we would print or something like that. The functions actually don't necessarily have to return anything. In fact, lots of Python functions that are employed in complicated software actually return nothing at all, but instead cause changes to the variables that are passed to the function itself, or even modify something that's defined outside of the function. So it's necessary in Python to specify explicitly what is returned by this function when it is called. Something specifies what's returned by len in the definition of len. And we do this with the keyword shown here in the example, and I'm going to type it here as well. The keyword is return. And then whatever precedes or whatever follows return is what is returned by our function when it's called. And in this case, if we want to return result, then we will say return result. There's a question in the chat. Is there a rule to the information that is written within and then in what's called the doc string? Yeah, so there's another component here that is technically not mandatory, though strongly encouraged. And that's the space in between the header and the body. And that is what's called the doc string, or the documentation string. And the doc string is a special kind of string. It's called a multi-line string. We've not worked with these today. We certainly will in Compusel. And a multi-line string is a string that can have multiple lines. I'm just going to make a little space below my working function. A multi-line string in general is a string that is specified within a set of 3 quotations. Now, S can be worked with just like any other string, except that with a multi-line string, it's implied by all of the returns. I can do this for as many lines as I want. And it's understood that within the actual data of this string, there are line returns. And according to wherever I return in my string. Now a doc string is like that. Yes, excellent point, Tareen. Antimony code is written using multi-line strings in Compusel. So there will be a few days where you get lots of practice with working with multi-line strings. Now in this case for doc strings, like shown here, doc strings are formatted as multi-line strings, and you'll notice when I start one of these in my IDE, PyCharm will automatically generate fields for me to fill out. But this data, this string, is not available inside the body of my function. Rather, what will happen is that IDEs like PyCharm or lots of peripheral Python tools can read those strings and actually automatically generate documentation about your code that's generated from the doc strings that you wrote. For example, I write this as a function and then come down here and say f equals is odd. Oftentimes you get things like when I pull up the documentation on this function, you'll notice it says this is a function, and it knows this from my doc string. So the doc strings are not mandatory, but highly encouraged and incredibly useful, both for yourself and for others. This is a Not a mandatory thing, but definitely an excellent way to keep track of what you're doing. It's a great way to communicate to others what the purpose of a function is. Oftentimes I write these just to keep track of what I'm trying to do as I'm developing functions and things like that. So for now, we'll just keep a little reference here. This is a function. And so now in this case, the function that I've prototyped here, this is complete. We've got a header that tells Python writing a function, specifies a name for my function, which is odd. I specify that my function can take one argument, which I'm referring to as I. And in my function will test whether or not the argument passed to it is odd, and then we'll return the result of that test. To question, what is the benefit of docstring over using the pound symbol for a comment? That's debatable. There are, for example, parsers that can generate documentation about code that's been written from comments. And in a lot of ways, there are ways to communicate with tools that you're using by actually specifying keyword commands in the comments. The standard for writing Python functions and classes is to include a multi-line docstring in Python 3. This has sort of been a refined process and sort of like structure over time, but there are a couple of different formats that you can follow. As you see here, this example here is a little bit older. I use a parser that works on this a little bit differently, so the comments that I write might look a little bit different from the comments that someone else writes. But the standard is to use the multi-line strings for documenting functions and classes. Excuse me. Okay, so now we have a workable function. And we can use this just like we've been using len or range or dir or anything else. So we can just test this and say print is odd 0. You notice when my command is too close to my function body, I get a warning here in my IDE, expected 2 blank lines after class or function definition. 2 blank lines meaning that there's no indentation in these 2 lines that follow my function definition. So this is how Python will understand not only the branches and say the logic and control flow, it will also understand developing infrastructure like this, like functions, or later for defining classes for custom data types. So when I print is odd of 0, I get false. For 1, I get true. 2, I get false. That's the basics of how to write just a very simple function. Now, there is a lot of complexity that begins from this point to do with functions. You can, for example, write a function within a function. For example, just like we were able to write, say, branches within branches when writing for loops and if statements and so on and so forth, we can also do things like write functions within functions. We can say within our function is odd, we can define another function that says, say we'll call it test. And test takes the argument called x, and we'll just return our actual test. The remainder of x divided by 2, does it not equal 0? In which case, we can just return test of I. And that is perfectly valid. You can also refer to functions and treat them like data, like they are objects. So I can say my function equals is odd. And then use this function that we've defined, but with this completely different, well, differently named reference. Say if we print my function of 3, and I still get true. Now, probably most complicated, at least easiest to complicate, is differences in what's called scope. I'm going to reverse all of this fancy business for now, since we have not much need for it at the moment. And instead, I'm going to point out this observation here. In our function, we've had this, let's say, at least in my case, I named the argument that can be passed into my function. I named it I. And I do my test on whatever's passed into my function by referring to it with the name I. Now, out here, after my function definition, when I go to actually use it, can I say I equals is odd of, say, 2? Is there any problem with that? They have the same name, but are they referring to the same thing? And the answer is they're not the same thing. In this case, I is defined within the body of this function. And the reason for that is because it's declared here as an argument in the function, and then is only defined within the body of the function. This is called the scope. I, in this case, as it's defined here in this argument, is only defined within the scope of the body of the function, and then afterward is no longer defined. It's not a real thing outside of the body of my function, whereas out here, outside of my function definition, I has absolutely nothing to do with the I that's named as my argument for my function. It's just referring to the return value of my function. So here may be named the same, but not referring to the same thing. And the difference in scope is what makes this possible. Now, here is something fun that has lots to do with this issue of variable scope. So this function that we've defined here, this is dividing by 2, testing the remainder and seeing if it is not equal to 0, and that's our test for whether or not our function is odd. Now, let's try another function. Let's call it, you want to follow along with me, let's call it, say, def and is divisible by. And we're going to have one argument for this function as well. Let's also call it, let's call it x. So our function is going to be named is divisible by, and it's going to have also one argument. We're going to name it x. Give it a doc string if you like. This is another function. And now what we're going to do is we're going to declare another result that we're going to return. But follow along carefully with what's done here. I'm going to declare a variable outside of my function, and before it, I'm going to call it b. I'm going to say b is equal to 2.0. So b is a float. It's equal to 2.0. And it's going to be declared before my new function is divisible by. Now, we'll go back into our function. Our new function is divisible by, and what we're going to return is the test of whether or not the passed argument x into our function, is it divisible by b. B being defined before the function, yet you'll notice that in the case of my IDE, I have something popping up highlighting this b when I click on it within the function and recognizing it from where it was declared before the function. And what that means, what is occurring here, is that variables defined in the what's called the outer scope, outside of the function, before it, that information is inherited into the scope of the function body. So anything that has been declared before my function, I can refer to varying degrees of whether or not you can actually change values or so on and so forth. You can refer to, say, previously defined functions, previously defined data, you can refer to that from within inside the actual body of new functions. So now I can say C equals is divisible by, say, 3.0. And now I can change how this function behaves, is divisible by. I can change how that function behaves by changing some of the data that was defined before the function definition. So for example, here, testing whether or not 3 is divisible by 2, 2 being defined up here for b, 3 being passed into the new function as an argument, and then the function actually doing the calculation to see if the passed argument is divisible by the previously defined data. When I run this, I get that it's false. Now you'll notice that when I change my passed argument to 4, 4 is divisible by b equals 2, so that's fine. If I change my argument back to 3, then change b also to equal 3, I get true again. Outer scope, then the data from that outer scope gets inherited into this inner scope. This is also true for functions that are defined within functions. So here, if I have a function defined within my function, for example, not only can b be referred to within my inner function, but so can x, because the function body of is divisible by is the outer scope for the function body of test. And so this information will propagate from here to here to here. Now, a lot of why we bring this up is because this causes, well, we know of instances where this has caused some major headaches when it comes to how to propagate information in model specification when we actually go to do some of the implementations for CompuCell Python. And so what we want to have right now is a working knowledge of how this information will pass from one scope to another, so that when we go to actually do our model specification, we don't find that things are getting strange as far as where variables are being modified, within functions and later in class definitions as well. Now, one thing to note here, as discussed a little bit earlier, functions don't necessarily have to return anything. Hence why we must, if we want our function to actually return something, we have to explicitly state what the returned thing is. And then the question arises, well, what happens if we don't specify anything? What if, say I do, and my new function is divisible by, if I do that calculation, but don't return anything, well then what is C? C here being a result of calling is divisible by 3.0. It was testing whether or not the value is divisible by whatever the value of B is. But now the function isn't returning anything. So what happens when I call this function and actually try to assign a value to it? And I find that when I assign that value to C and then print C, I get none. So this is one of the many examples of why none is so special and sort of ubiquitous across not just Python, but programming languages in general. Sort of the idea of referring to something like nothing. And in this case, when returning nothing from a function, something is returned. The thing that is returned is none. And of course, this can be used in things like control flow and things like that. So one can say, we go back and fix our function and say this is actually returning something now. Well, this is a Boolean that's being returned, which means that these functions can then be used as conditionals and so on and so forth. Or in the case of if returning nothing, you can say if the return value of my function is none, so on and so forth. All right, so I'd like to let me check my time real quick. Okay, so I'd actually like to give everyone 5 minutes or so and work out this exercise. The exercise is write a function that calculates the nth Fibonacci number. The definition of which is shown here for your convenience. So this is a piecewise definition. For n equals 0, the value is 0. For n equals 1, the value is 1. And for all n greater than 1, there's a recursive definition here. So I'll give everyone 5 minutes. Maybe try at that a little bit, see how it goes, and then we'll reconvene. All right. Let's see how everyone is doing. We took a poll a couple, yeah, there we go. All right, so I think we still have some people working. We'll give it another, yeah, there's another poll going. Give everyone a couple more minutes. All right. Let's go through this together. I'm gonna go ahead and just clear my script here and start fresh. I'm gonna start by just naming a function. It's customary to give things simple names. Helps understand complicated ideas. Let's just name a new function, say def, and call it fib. And the equations on the slide refer to the nth number. So let's say we're going to take one argument n and start our body by concluding the header with a colon. I'm going to make a tiny doc string, just n fib number, and start the actual calculations. So you have three cases here. Actually, we have four cases, but we'll deal with the ones that are expressed here mathematically. That is that we have some branching to do according to the input that we get that's passed to our function. Namely, that if n is equal to 0, then the number we would like to return, according to the definition, if n equals 0, then the Fibonacci number for n equals 0 is 0. In a Python function, you can declare, excuse me, return at multiple points in the function body, just under the pretense that writing something after a return function within the same level of indentation isn't going to do anything, because at this level, in this branch, after return has been called, nothing else executes. The program will return whatever is returned and continue on outside of the function. But otherwise, it's perfectly valid to say that in a branch, you can just simply return a value. And also, in another branch, say when n equals 1, which we implement as elif, and then the condition n equals 1. In this case, the definition says when n equals 1, the Fibonacci number is 1. And lastly, at least as far as implementing our definition, good practice, we'll just say else, meaning for all other cases. And now we're going to return something. And the question is, what is it that we actually return? In the case of the Fibonacci number definition, we actually calculate other Fibonacci numbers. In this case, we can do something like this. Our function is defining the nth Fibonacci number, so we can just say return a call to our function with different values passed as arguments. This function, fib, calls itself. And so long as nothing in the actual flow of logic with doing these calculations results in an infinite recursion, meaning that the function just repeatedly calls itself over and over and over, then this is perfectly valid. Now, what's not valid here is, say, what happens when I pass a negative number to fib? Or what happens when I pass a float? Because one thing to note about Python is that by default, no constraints are placed on anything that's passed around as to what type of data it has to be. This is, I won't say both a strength and weakness, but this is a perk and also a burden of working with Python, is that nothing per se necessitates what has to be passed into this function, except that something has to be passed in. And for any enforcement of the characteristics of the data that can be passed, we must enforce explicitly. For example, we can prevent our function from trying to execute and instead notify the user through an error or a warning. We can prevent executing when the passed argument is negative by first checking and saying if n is less than 0, and then we're going to generate an error. We've seen errors earlier today. We saw things like type errors. We saw things like value error. It's very straightforward to be able to create and then throw an error yourself in your own code. And you can do this with the keyword raise. There are lots of predefined types of exceptions that can be thrown. These are all just mostly implying information about the type of error that's been raised, or exception that's been raised. All of them come from the same type of exception, just called exception. So in this case, we can be a little bit informative, and let's say that if someone passes a negative value into our function, we can raise a value error. And a value is a type. Value error is a type, excuse me. And when we pass to it a string, say cannot be negative. And what we'll find is that if we pass a negative number to our function, it won't try to calculate. say fib -1, we get a value error. Cannot be negative. Can be even more rigorous in our checks, which is not a bad idea for having a recursive definition like this, by also using a built-in function to do type checking. And the function is called isInstance. isInstance takes 2 arguments and returns a bool, and it tests whether or not something that's been passed to it is of a data type that's also passed. And what I mean by that is we can say if not isInstance, meaning the negation of the result of isInstance, and say pass the argument that's been passed into our function in and the type to test against, which is int. Say if in is not an instance of the int type, and we can raise another error. Raise type error. Not an int. And so now try to calculate the nth Fibonacci number of the string in, then get a type error, not an int. This is how all of this is implemented, and everything that you work with in Python when coming across these errors, you find these all the time. It'll usually be what's called a traceback provided that will give you information about where the error was or the exception was thrown, like in here, and how that all propagated through the information with calls across lots of scripts and functions and so on and so forth. It all boils down to just increasing complexity of these same types of structures.
If I may make a small parenthesis, the error you got actually was before your raise.
It was. Yeah, this is an excellent point, Giuliano. Thank you. So now you'll notice here, Giuliano's pointed out that I did get a type error, and I didn't notice because I wrote in a type error to be raised that the type error I got was actually not the type error that I myself raised, but rather at line 5. The issue here being that a string type was passed into the function fib, and then the first thing that was calculated was a test for whether or not a string is less than the int 0. And then, as Giuliano pointed out, there is no comparison defined between a string, which is what was passed, and an int, which is what was being tested against. And so what's necessary to do here is to reverse the order. First, we must test whether or not an int was passed into the function in the first place, and if it was not, then we throw an error and nothing else occurs in our function. Having validated the type, then we can test to make sure that it's in proper domain for the Fibonacci numbers by raising a value error if it's not, in which case the function stops evaluating. Now, having passed all of our checks, type fib of, say, 5 and print it. $12, $16, should get numbers that you can well validate against Wikipedia or your favorite discrete mathematics textbook. So I'll leave this up for a little bit longer. I can also make this available, but this would be something like a final solution that exercises quite a lot of what we've crashed through today so far. All right. Now, very quickly, we're going to get a little more, we're going to learn this more through practice, both later today and throughout the week than we'll really spend much time on today. But I think I've seen a question to this effect in the chat as well, which is modules, how to get stuff into our script to be able to use when writing software. For example, we have built-in functions like range, len, dir, and then types that are known like strings, ints, floats, so on and so forth. What about other stuff? Say something that I wrote that you would like to use in your script, or say something that's distributed in your Python environment like Tellurium. Import Tellurium as TE. Many of you have been looking at that line at the top of your Jupyter notebook since this morning. And this is done through modules. So we've defined, for example, a function in this script. The name of my script is just called scratch.py. Now, if I'm in another script, it's possible for me to write something like what many of you have with your Tellurium import statement. It's possible to write something like from scratch, my script, import fib, which is to say that the definitions that are defined in this script or in some script or set of scripts defined by someone else to take information like functions, data values, data types, and import them into what I'm currently developing. And we saw this in our first example today when importing Tellurium with te.load a and so on and so forth. Much of even the Python library, you can try this out now, much of the Python library, well, the Python library is distributed along, is distributed along with a Python, in a Python environment, which means that if you have Python available to you like you do right now, then you can test out importing from modules right now. And there are a lot of them. So for example, say you'd like to calculate the square root of something. You have one way of being able to do that, which is say x equals, and we can say 2 and to the power of 0.5. If you recall from earlier this morning, the power operator being 2 asterisks. Square root is taking something to the power of 0.5. Another way of doing this is in a library that's distributed with the Python, it's called interpreter, and that library is called the math library. And you can do something like this. From math, import sqrt, which is the square root function, which somewhere has defined some def square root and an argument. That function is defined in the math module. In which case I can also say y equals square root of 2. Scripts like what we've written today with defining new functions, as well as with the exercises that we'll do in our next module for defining classes, and later this week, this coming week, for the actual model specification that we do with all of the different modules. It's possible to take the definitions of those functions, those types, those calculations, so on and so forth, and import them from some other Python script where they're defined into the Python script that you're working on. And then you can define new definitions that build off of those definitions, or work with those predefined types. You can specify then functions here in new scripts that then can be used in other scripts. So you can sort of break up, the operations and the procedures and the definitions according to, whatever project you may be working on, but break it up into more manageable chunks of simpler tasks, simpler definitions, simpler data types, and be able to sort of construct things in this, sort of virtual reality of definitions and objects and types and so on and so forth. And much of that is done by treating Python scripts as modules and importing definitions from one script into another using this sort of functionality. Now, this can get fairly nuanced and at times quite subtle. For example, and we'll get a little more practice with this in the next module, you'll often find that when working with modules, you can find things like from math, maybe math isn't a good example. From SciPy dot. And now there are things into this package called SciPy with sub packages, stats, FFT for fast Fourier transform, cluster. If I do stats and then dot, and now I have more things. So this is directory structures. The directory SciPy, subdirectory stats, and then within stats, there are all of these scripts that have actual definitions that can then be imported into this script. So navigation for importing and so on and so forth in Python is done using these dots. For all the built-in libraries like math, there are no dots necessary. Python always knows where they are, so you don't have to worry about any of that. All right, well, now we may go over with the rest of this because as was mentioned earlier today, dictionaries, arguably the most heavily used of the types in CompuCell-based modeling. Dictionaries are a very particular type and a very useful one for many reasons in general, as well as in the type of work that we're going to do this week and that we'll often do when doing CompuCell-based modeling and Python-based modeling in general. And dictionaries are special because dictionaries are in some senses like lists or tuples or strings, some kind of sequence, in that with the sequences, there's a one-dimensional structure where we always have the capability to be able to specify an index. And with an index or with a slice, be able to access elements in our sequence. The index 0 being the first element, the index -1 being the last element. Dictionaries are special, again, for a lot of reasons, but one of the reasons they're extremely useful is because with a Python dictionary, you specify what could be thought of as the index for a value in a dictionary. So instead of doing something like passing an integer to a bracket on a dictionary, say I have some dictionaries, just going to call it my dictionary. Dictionaries can be instantiated using curly brackets. So square brackets were lists, parentheses were tuples, dictionaries are curly brackets. And now, whereas in the lists or the tuples or also the strings, we could just start specifying data in a sequence and an order would be followed according to the order of the inputs. Dictionaries can instead specify what's called a key. And a key will act like an index on a list, except that the key is also data. For example, I can specify a dictionary and specify pairs of keys by which I can index something, and then a corresponding value that corresponds to that key. And I do this using first a declaration of the key. Say I want to have a key of 5. And I would like to have a corresponding value of the string A, and I can specify this using a colon. 5 here is the key, A key, excuse me, and then A is the value of the dictionary that corresponds to the key 5. The key is unique for the dictionary. The value is not, in that I can specify a key also equal to the string A. And with that key goes a corresponding value of, say, 6. Here now, the key 5 in my dictionary corresponds to a value of the string A, and the key that is the string A corresponds to a value of 6. And this can be used as follows. So now that this declaration has been made, I can say my dictionary, and when I use a square bracket like a list, but instead pass the string A, anyone have a guess as to what I'll get? About 6. The value in a dictionary that corresponds to a particular key. Here in the picture in this slide, Anna is a key that corresponds to a value of B. Denise is a key that corresponds to a value of A. John, a key, A plus is a value. Katie is a key, A is another value. And the values can then be referenced by their corresponding keys. Notice that this is heterogeneous data. I've got an int being used here as a key, and then a string as a value, and then a string as a key, and an int as a value. This is pretty non-restrictive. Can get very complicated when it comes to custom data types, but for everything that we'll be interested in for this week, all of it can be used for keys or values in dictionaries. So if we test this out and say print the value of the dictionary that corresponds to the key A, we already know we'll get 6 as defined here. And likewise, we should find that the value that corresponds to a key of 5 in my dictionary, is defined here, should return A. Question in the chat: is there any way to make a dictionary by transposing 2 lists? So if I had something like, I don't think I understand. Yeah, thank you, Jim. Yeah, so with having, say, something like 2 lists, you have A equals 1, 2, and 3, and B equals 2, 3, and 4, then it's possible to do things like for AI and A, and for BI and B, my dictionary of AI equals BI.
I don't think that would do quite what you wanted. Would it?
Yeah, so what this
Because
is,
you want to pair, you want to walk it step by step through. So you want the ith index of the.
yeah, so what you'll notice here is that values, you can have, say, multiple values all corresponding to the same value throughout a dictionary, whereas the keys in a dictionary are unique in that when doing these sorts of iterations, one cannot specify multiple values to a single key in a dictionary. So if I do something like reverse this ordering, where I'm iterating over B for every element in A, and I'm assigning AI to BI, accessing BI multiple times and assigning different values to it, and that's overwriting the same to the same key, placing different values that correspond to that same key. So you can see an example of that here. And yeah, Giuliano, yeah, brings up zip. Zip has nice functionality to be able to do paired iterations like this. This is the sort of thing you can do 1,000 different ways. Now, there are some, as you might expect, dare I say, hope for, lots of operations defined on dictionaries. So there's, of course, the built-in operation of actually doing lookup, which is to say getting a value that corresponds to a particular key with the corresponding exception key error, which is thrown when trying to access a key that is not defined for a dictionary. So my dictionary has defined values for the keys that are the int 5 and the string A. And you'll notice here in line 3, I tried to access the value corresponding to the int A or int 4, and that's not defined. And so I get a key error. And it tells me what the key was that I tried to look up, and the program terminates. Now, with that in mind, keys and values can be assigned to dictionaries dynamically, in that this line that I just attempted, which is to say, get the value in my dictionary that corresponds to a key of 4, this throws an error because that's not been defined. Whereas what I can say is that I would like to declare a new key in my dictionary with the corresponding value. In this case, I'm going to say that along with my initial definition, I'm also going to then add a new value that is a string that says new value, and that's going to correspond to a key of the integer 4. So you can add keys and values dynamically like this. You can do things like tests and iterations. So there are a couple of different ways to do iterations over the data that's defined in dictionaries. One can, for example, get all of the keys in a dictionary by using the function defined on the dictionary called keys. And one can iterate over these, for example, in a for loop as follows. One can say for k in my dictionary dot keys, and then just print k and see what's going on in k right now. K has the keys 5, A, and 4. You can also do things like, say, generate a list of the keys by saying my keys equals, and let's pass to the actual list type, my dictionary dot keys. And when we print my keys, now we have a list that corresponds to all of the keys in the dictionary. You can also ask things like, for example, let's print the result of the test. Let's see if 6 is in my dictionary. We see we get a Boolean. Test for whether or not 6 is in my dictionary. Now let's see if, say, 5 is in my dictionary. It sure is. And now let's see if A, the string A, you see that it's false. Now the thing is, A is in my dictionary, but it's a value, not a key. And so you'll see here that a test like this, when asking, is something in a dictionary, what one is really asking is something a key in the dictionary? Not a value, or not a key or value, but is it a key? Now, just like in lists, you can delete elements in a couple of different ways. There's, of course, the del element that we sort of blasted by when discussing lists. And so to delete a particular element, we can reference it by key. Say, for example, added here dynamically the string new value with much enthusiasm, and assign that to a key of 4, and then we can just go through and delete that with the del. Added it, removed it, Just like the keys argument, you can also get the values in a dictionary, much like the keys argument, except the function is values. A6, new value. And just like the keys, it can also construct a list, so on and so forth. This can also be iterated over. So now expanding on this a little bit with these built-in, what are called iterables. Let's do one more, and that is a very useful function to find on dictionaries. The function is called items. And items actually iterates returning a tuple. And that tuple is every key and value in a dictionary. Meaning every key value pair defined in a dictionary. So here, when we say for K, comma V, this is a tuple. In my dictionary.items, what this is saying is for every pair of key and value. And so when I say print this, I get every key, 5 and A, B and 6, 4 and new value. Another particularity that's important to note about dictionaries is that the data in a dictionary, while each key and value are paired, the ordering of key value pairs for the standard dictionary is not particular. It does not make any difference how you order the inputs of data when adding them dynamically. The actual ordering in memory for dictionaries is not guaranteed, whereas in lists it is. When you build a list with a particular order, the order of that list, unless modified by you or someone else, is respected, and that is not the case with dictionaries. Again, there can be duplicate values in a dictionary, but the keys must be unique because they are something like indices. And we won't get too much into I don't want to get into the weeds on this detail, but the requirement for whether or not something can be stored inside a dictionary, the criterion is that it must be what's called hashable. And I don't want to dive into the details on that right now, but in general, if you find that you can't load something into a dictionary and it's causing some sort of error, it has everything to do with whether or not the object you're trying to put in a dictionary is hashable. Okay, we've done most of this. Like the lists and tuples and strings, there are lots of other definitions defined. For example, we'll just close out with this, and I'll leave up this exercise for those of you who would like to work through the break. For example, if we would like to, say, remove a key and value from a dictionary, the dictionary has a method called pop. And much like the list, we will pass the key that we would like to have removed or popped from the dictionary. So if I say pass my dictionary and pop, I'm going to pass the key that I would like to remove. from my dictionary. And when I print it, there you go. It's got 5 and A, and then 4 and new value, but no B and 6. I think I'm gonna open it up for survey now. We've got a couple of minutes. Yeah, James, let's open up questioning, see how things are going. Want to check in with everyone. There was a lot of blasting past material. I want to make sure everyone's okay. Looks like we've got most responses in. Great. Okay, so let's go ahead and do our 15-minute break now. And then I'll leave this up, and when we return in 15 minutes, we'll just blast through. I have to do this very quickly. And then we'll start on our last module for the day, honing in on how to write our own types of data, which maybe, well, I won't even preview it. We'll get into it when we get there. Okay. James, unless you have any parting words, I'm gonna adjourn us for a 15-minute break.
Okay, just take a minute to fill out the questionnaire if you would. That would be great.
All right, thank you very much. See you all. Let's do 2 till 4 Eastern time. Just make it an even 4 o'clock. See you all then. All right. It's 1 till, so I'll give a 1-minute warning. Give everyone a little bit of time to settle back in. And then we will get to our 4th and final module for the day. Then everyone can go off and have dreams of data types and custom Python functions and modules. As funny as that may sound for anyone who's worked a lot in programming, it's not as strange as you you might think. But anyway, so 4 o'clock Indiana time. So let's pick back up. Before we begin, just a couple of reminders. First, this last module is scheduled to end at around 5:30 p.m. Eastern. We'll see how that goes. We may go a little early, just depending on how we get through things. No problem either way. But after that, we do have scheduled a closing block of time, sort of an open forum to ask questions, gather any necessary information that you might need given your experience today, or any other lingering questions you might have about the actual workshop that starts tomorrow, which again is at 10 a.m. Eastern time. That'll be the same every day throughout the entire workshop. And I would also like to remind you that we have our workshops, or a hackathon, excuse me. We have a hackathon scheduled for the last 2 days after the workshop. Of course, again, we invite those of you who may have project ideas in mind, to participate, to have one slide summaries ready to be able to share that with the rest of the workshop, both for our reference and for the reference of others, in particular for those who don't have a hackathon idea, but who would like to participate in the hackathon. Of course, that's not only acceptable, but encouraged. So we welcome participation by those who are interested, whether they do or do not have a specific project in mind.
And if you develop ideas during the week, and that means you have an idea that comes to you after Tuesday, that's fine too. We'll have a second opportunity to pitch your ideas on Thursday and Saturday morning as well. So don't feel that you're ever left out from working in the project.
Great, thank you for that, James. Now, before we start in on our last module, I'd like to go through this exercise that was left up. So for those of you who may have worked through this on the break, I'd like to go through this very quickly. Again, these slides are now available in the shared Google Drive. So we have a running collection of all of the slides that will be delivered in the various modules this week, and that includes our day 0 today. So everything is now uploaded as it has been discussed in our time together today, including this slide here. So anything that we may have skipped over or blasted through, maybe the caffeine got me going a little fast, it happens. And so those slides are available for your reference. And the link has been passed around in the chat a few times. I'm gonna lean on some of my supporting crew to grab that link while I start in on this exercise. And that exercise uses just about everything we discussed in module 3, not including the actual modules, but rather focusing on dictionaries and functions. So we'd like to say write a function that will take as argument a string and will return a dictionary that reports the number of occurrences of every character in the string that was passed as argument. And so let's do that real quick. So I'm just gonna clear my Scratch script here, and I'm gonna start a new function with the keyword def, and I'm gonna name my function count_car. And it's gonna take one argument. I'm just gonna name that argument S. S for string. And I'm going to conclude the heading, write a small little doc string, and all it says is this function counts characters. That's the end of my doc string. And then I'm going to start on the body. And the body is going to return a dictionary. So let's go ahead and declare an empty dictionary. Well, let's name it result. So we'll say result equals and empty curly brackets. Result is the dictionary that we're going to populate with the number of occurrences of every character in the string that's passed to our function. And now we can first do this by, I'm going to make some comments here because we're going to divide this up into two subtasks. Again, you can put a comment into your code using the pound, just Shift-3. The first thing we're going to do is get the unique characters in the string that was passed to our function. So that's task number one, get unique characters. And we can return twice, and let's go ahead and put in a second comment. Shift-3, second comment, count, just say count characters. So those are our two tasks. Now for our first task, for getting the unique characters in our string, let's just start a new variable. Let's declare an empty list. We'll call that list, say name it unique cars, and empty list is equal to an empty square bracket set. And now what we're going to do is we're going to iterate over every element of our string sequence for, let's say, SS in S. So for every element SS in our sequence S, we're just going to say if the element is not in our unique cars list, then append it. So for every character in the past string S, if that character is not in our list called unique cars, then append that character to our list of unique cars. And that's our first task accomplished. Secondly, now we're just going to go through and we're going to count the number of occurrences of every element in unique cars, number of occurrences in the original string that was passed. And we can do this as follows. Now let's iterate through every character in unique cars. We can use the same name for our iterator for SS in unique cars. And the first thing that we'll do is we'll declare a key of that unique character, SS. We'll declare that as a key in our, our result dictionary. Result will be the dictionary that we return. We'll say result with the key of SS equal to an element in our unique cars, and let's just initialize that as equal to 0, and then we'll do a loop over the string that was passed and count the number of times that an element in S is equal to SS in unique cars. And that looks like this. Let's say for X in our original past argument, for X in S, if X is equal to SS, X is an element in the original argument, SS is the unique character in our list of unique characters, and if X is equal to SS, then result of SS, the value that goes with the key that is our unique character, I'm just going to increase it by a value of 1. Again, there are a number of ways to do this. This is one that exercises lots of what we've learned today. Probably, if you're feeling creative and confident, you could potentially generate a solution here that's about 4 lines long, and that's totally fine. We're going to do this explicitly to sort of work our chops on what we've learned. And so now in this case, we've looped over every unique character that was found, initialized a summation that corresponds to each of those unique characters, and then counted the number of times we find in our original past argument S, how many times that's equal to the unique character that we're considering. And lastly, return it. Return result. So that's what it looks like. Give it another 30 seconds or so. I see we got one response of someone needing help. Feel free to raise a hand or reach out and we can connect. If not in here, maybe we can move that support over to a breakout room. In the meantime, we can test this. So pick your favorite string or generate some nonsense in one. Doesn't matter. I'm going to print the return value of my new function, and I'm just going to do A, B, 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 C, C, D. And remember, 2 lines of indentation equal to the indentation at which the function was defined in the first place. That lets Python know that the body of the function being defined is done. And I'm just going to test this out, see if it works. And there you go. So you'll find that the return dictionary will specify every character found in the past string as a key, A, B, C, D. Then the corresponding value that goes with each of those keys is equal to the number of occurrences of that key or of that character in the string that was passed. 4 A's, 3 B's, 2 C's, and 1 D in my test case. Now, of course, you can find a multi-line string of some Shakespeare, then you could run the exact same thing and do the same sort of analysis on some sort of a real world problem, not just some gibberish in a string. All the same, see, most are done. Got a few who need a little more time, and I think I still see the same response of someone needing help. So again, if you want to reach out to either James or me or in private chat, we can move you over to a break room and maybe work with Giuliano if he's available, get you back on track. I'll leave that up for everyone's reference and just give it a couple of minutes. All right. Okay. So for those of you who may be joining a little bit late, with getting back, no problem. Up until now, we've gone through this exercise that concluded module 3. So this was an exercise that was left up for anyone who wanted to continue working during the break. And then we just went through this together very quickly. So we've defined a function here that counts the number of occurrences of the unique characters in a string that's passed to the function and just returns that as a dictionary. So we're gonna now move to module 4. Of course, anyone who may be struggling with this, the slides will be available. Some code that more or less demonstrates this will also be available. And of course, in the very least, feel free to reach out to one of us about going through this if anything's unclear. Don't need to be able to do this to progress through our last module. Though there are a lot of things in here certainly worth practicing that'll be helpful for the upcoming week. So with that in mind, I'd like to go on to module 4. And module 4 is, in my opinion, the most fun. Also tends to be the scariest for people coming into programming in general. So for those of you who have, say, coming into this with experience in other languages, class development or writing classes and data types is perhaps something that's familiar to you, at least in principle. For others who are just coming at this, totally from scratch, this can be a little strange to think about at times. But this module will focus on designing custom types. We've been, say, working with our ints, integers. We've been working with our floats, our lists, and other sequences, and now our dictionaries. They, have methods that are defined on them, like extend for lists or pop for both dictionaries and lists. And there are definitions that define those. Int and float and list and dictionary, those are classes. They have class definitions, and those class definitions define those types, defines the methods that we can use, like extend defines what happens when, say, we call len, len, len on, say, a dictionary. The specification of what describes those behaviors, all of those methods that are available to us and those attributes, they're available to us as well to be able to design our own types, which, as you'll find this coming week in the Multicell workshop, is incredibly useful for a number of applications. In our case, very useful for being able to generate models that are compatible with the simulator. The notion of designing custom classes is leveraged in Multicell and is at the very core of model specification using Python. And for as maybe abstract as that may sound to some people, it actually generates a way for us to be able to do rather complicated things in a very simple way. And so we're going to explore some very basic aspects of that now, so that in this coming week, when we go to actually do this stuff in Python for Multicell, some of the ideas might not be so foreign. So we're going to talk about classes. And when we talk about classes, we have to make this distinction between, and maybe this is a working concept now for everyone, which is great. But the distinction here is important to make, that we talk about things like types, ints, floats, strings, versus objects. And when we've been doing all of these little test scripts, A equals 1, B equals, a list, so on and so forth, every time that we instantiate something, what we've created is an object. And that object has data on your computer or on a server, if you're using NanoHub. And the data that corresponds to that object is according to its type. And the type defines not only the data that makes up an object, but also defines the ways in which that object can be interacted with. For example, extend, pop, append, remove. All of those methods defined on list, all part of the class definition that defines the list type. And we can create lots of instances of, say, lists or bools, but all of them are the same type. They all have the same methods. They may have different underlying data. You can have ints, lots of ints with lots of different values, but every int will have the same operators defined for it, and so on and so forth. So object versus type. Every object is an instance of some type. All right. So with that distinction, I just talked through like 5 of my slides. That's fine. Got an example here prepared that probably the point is already well made. So the thing about defining classes, and I don't want to get very much into this because in this coming week, we will do a little bit of actual design of classes, and that we can define the way that data is stored in our models. When we implement models in CompuCell, we'll have data that we'll be interested in, and we'll be interested in storing it in different ways and performing different types of typical manipulations on it, and so on and so forth. And we'll do that through methods that are defined through class definition. And so it's important here to think at least a little bit about that. Part of the sort of worldview of class design is to define what types of actual underlying data make up a class or an instance of a class. And then think about the methods that are presented for operations on those instances, and how those operations actually affect the underlying data. And as an example, you think of that we've been creating lists of different elements, and those are ordered. And you can ask the question, why is a list order specific, but a dictionary isn't? And of course, the obvious example is because the person who designed the list designed it to be order specific, and vice versa for the case of the dictionary. But in the actual implementation, and this will be important to some extent when we actually go to do our CompuCell Python, is that there are corresponding types of operations that are defined on the class that make those properties available. Like in the case of the list, having the data having a specific order. All of these different methods, they all operate around this sort of internal representation for the case of the list, that for every element in the list, there is a reference to the next element in the list. And that referencing scheme is what makes a list ordered. We can do similar things for whatever sorts of things we may want to implement in our models when we do CompuCell models. But what's important here to recognize is that there are internal calculations that will occur for instances of a type that make the sort of available methods and calculations both available and happen. And so with all of that ado out of the way, let's just go here for a second, and then we're going to actually do a little bit of coding. So one of the probably most complicated parts of working with classes, and I also only bring this up because we will use it this coming week. Every time we use anything CompuCell Python, this notion will come up from pretty much day one, is the idea of class hierarchies and what's called inheritance. And that is to say that for every class that we may design, for every, say, custom type that we're going to create, what we can do is base the definition of a class on a definition of another class. In that, if I have, say, something like an existing class definition for an animal with methods on it, like where is it, or is it asleep, or I don't know, is it on Earth? It's then possible to take that class definition for an animal and use it as what's called a parent class, or some people call it a superclass, and write a new definition for a class based on that parent class, such that what's called the child class, the class that inherits from the parent class, gets all of the definitions that are defined for the parent class on it, and then can add more things. So if my, say, animal class definition has a function defined on it that tells me whether or not an instance of the animal is on Earth or on Mars, when I inherit that class definition when defining some new class called person, I automatically get that function on Earth, on Mars, whatever, defined on my person class, or say a cat class or rabbit, and so on and so forth. So there's this notion of inheriting these abstract ideas from a parent class to a child class, such that we can sort of abstract away a lot of the things that either are very basic across, say, a modeling platform that we may be interested in building, and then can sort of like template out that functionality onto particular instances. We do this a lot in some of the research that we do in CompuCell, but at its very heart, we do this every day with building CompuCell Python models in general. We get a lot of practice on this throughout the week. So, but what I would like to do is sort of get that idea into everyone's head now who may not be necessarily familiar with it. And maybe it'll be a little more clear when we actually go to design our first class. So let's make a class. I'm going to split my screen here. Again, don't worry if you didn't get this function from the end of module 3. Some code will be provided as well as the slides for your reference. Let's make a class. So defining a class has some of the same procedures as defining a function, except that a function is just a function. We can call it, we can get something from it, we pass things into it. Whereas with a class, we're actually using this as a prototype to create things in data, potentially lots of instances of a type in the actual memory of our computer. So, but we're going to start it similarly to how we start a definition, and that is that a class also has a header, and that header begins with the keyword, maybe you guessed it, class. And the name that we would like to assign to our class is specified next. We use just a simple example here of defining something like a coordinate. Say a 2D coordinate. So let's call our new class coordinate. I like this example because you think of coordinates in, say, two-dimensional Cartesian space, something like a vector. You have something like an x coordinate and a y coordinate, and the combination of those two describes a coordinate. We're going to create a custom class that represents that idea. Now, if we have a parent class that we would like to inherit from, we can specify the parent class after the name of the class that we're developing, and we name the parent class in parentheses. Now, in this example here on the right, and I'm going to follow this as we go through it as well, what's shown here is that this class coordinate is inheriting from a class called object. But you'll notice if you refer to my screen that object is shaded in the same color as like what you see for len or dir or for the string constructor. And that's because object is a built-in class in Python. And in fact, object is the base, like the ultimate parent class of all classes. That it's possible to have this sprawling hierarchy of an infinite number of layers of classes inheriting from more classes and more classes than you could possibly get your head around. But what you will find is that when you trace your way up the hierarchy, eventually you'll find that something is the child of object. And hence in Python 3, this declaration is actually not necessary. So if not inheriting from something else, the assumption is made without this declaration that one would like to inherit from the object class. But we'll write it here just to get the practice of writing something like inheriting from a parent class. Now, after we finish our header, we can terminate it with a colon, and then like the function definition, we'll start the class body, and that will consist of returning one line and then starting a new level of indentation. So this is like the defining the class body. Everything that's within one level of indentation will be considered as part of the class body until two lines are found at the original level of indentation at which the class definition began. And now we're going to give some personality, and by that I mean some characteristics or what are called attributes as well as methods to our coordinate class. And so to begin, there are specifically two things about classes that are intrinsic to their definitions. The first being simpler of the two, I think, maybe the more complicated, I guess depends on who you ask. But the first type of object feature, I guess would be the word. The first type of feature that belongs to a class definition is what's called an attribute. And an attribute is data that belongs to an instance of the class. And by that, what I mean is that we can assign data like, say, an x coordinate, a y coordinate. we can assign that internal data as attributes to every instance of our coordinate class. And for every instance that we create, each will have underlying data that corresponds to the attributes that we define on the class definition. So that's the first type of feature for coordinates. And there's no limit on how many attributes you give to a class. The only limit is that they must be uniquely named for the class. Just like overriding the name of a variable, the same is true for defining attributes for a class. And we'll go through how to actually do that here in a second. But secondly, the second characteristic feature of a class is a method. And a method is like a function, except, maybe you guessed it, a method is a function defined on a class, like append for list. So all of the functions that are made available to us that are defined on all the types that we've worked with so far, those are implemented as what are called methods. And from our experience, we know that we can take an instance of some type, and then after referring to its name and then typing a dot, then we can refer to the methods like append or pop. So we can do that on the basis of individual instances of a particular class. There's a lot more to this, and we're going to neglect it for now. However, if you are interested in knowing more about this, there are actually lots of there's a whole variety of methods that you can define for classes. So if you'd like to know more about that, there's a whole variety of actually both attributes and methods. And I'd be happy to provide some resources to those of you who may be interested in some of those details. But for now, let's start by defining how to, let's figure out how to describe what happens when an instance of our class is created. What's a part of every class definition is a set of descriptors for basically instructions for what to do during certain operations on our class, like creating an instance of it. So when we have been doing things like x equals list, there are instructions to describe what happens when a list is created. And we can do that for our class as well. And we can do that with a specially named function called init, where init is both preceded by and followed by 2 underscores. You see my IDE will highlight it or show it as hot pink or magenta, depending on how easy color. And it's highlighted as such because it's very special. And it's special because this is the function that will be called when an instance of our class is created. Underscore, underscore, init, underscore, underscore. And init, like all typical methods on a class, will always take an argument as its first argument that is also very special. And you see my IDE will populate the argument automatically for me, and that very special argument is called self. Now, we didn't cover this much, if at all, when we were going through functions in the previous module, but you can see an example of it here. You can specify an arbitrary number of arguments for functions just by using a comma separated list. So something that looks like a tuple. It's not a tuple. Just everything that I name in a comma separated list, each of these are arguments that would be passed into, in this case, the actual constructor of my type in general. But for now, let's just keep it very simple and deal with this idea of self. And again, self will be the first argument in every method, excluding the variety of methods available that we won't deal with today, or really much this week that I can think of. Outside of our self argument, which we'll address in a second, let's say that to create one of our coordinate types, if we say we're talking about two-dimensional space for our coordinate, let's say that to create a coordinate, one has to give an x and y value, those corresponding to, say, an x or a coordinate along an x-axis and then a corresponding coordinate along a y-axis. And what we'd like to do is have our coordinate class have underlying data that consists of those x and y coordinates. And so how do we attach these values that are given during the creation of a coordinate? How do we store that in an instance of a coordinate class? Because again, we can create lots and lots of instances of coordinates, and we need to, provide instructions for how to store these x and y values for every instance of a coordinate class. And we can do that with self. Self, in every typical class method that we'll deal with, self is a reference to an instance of this class. In that when I say something like self.x equals x, x being the argument that was passed into my init function, self being this very special and sometimes mysterious for some argument that's passed as the first argument. When I say self.x, what I mean is that when doing instructions on an instance of my coordinate class, self refers to the instance for which the instructions are being carried out. And so when I do something like, say, C1 equals coordinate, and I pass 0 and 1, this is creating a coordinate, an instance of my coordinate class. What's happening here is that when this instance C1 is being created in the first place, a value of 0 is being passed to the named argument x in the init function, and that value of 0 is being stored as an attribute for the C1 instance, and it's being stored with the name x. In which case now what I can do is things like maybe what we've done a little bit already throughout the day, and that is I can refer to this named attribute x because it was defined on the coordinate class as an attribute using this declaration. When in the init function I say self.x equals something, that automatically adds an attribute named x to every instance of my coordinate class, in which case I can say print c1.x. And when I do that, I get a 0. 0 was passed to the named argument x, which was stored as a named attribute with the name of x on an instance that was created, and I can refer to that with the same name. You'll notice that my IDE even highlights the attribute within the init function, c1.x gets highlighted for self.x because self refers to whatever instance is being operated on. And so likewise, we can also say self.y equals y, and you guessed it, print c1.x and c1.y. I get 0 and 1. Specifying attributes on a class is as simple as that. Question about these coordinates. Self could be a geographical location or a specific location in a blood vessel. Absolutely. And in fact, doing that sort of abstraction with classes, I would say is one of the most powerful applications of using class definitions and class design. So if we're all good there, I often find that people find this elusively simple in the sense that this creation of attributes by just simply declaring them on this self variable, it almost seems like there's not enough work involved, or that something else needs to occur. But quite literally, declaring these attributes on self in the init function automatically does this for every instance of our class that's created. And we're not restricted to declaring, only attributes that say correspond to things that have been passed. We can just make up nonsense if we want to. Self.garbage equals none. Doesn't mean anything, but now coordinate has an attribute called garbage. And when the class is, or when an instance is created, the attribute of garbage will be initialized is equal to none. Simple as that. And question, so in this example, C1 is within the definition of self. So when C1 is being created during this call, self is referring to C1. So I think I want to answer your question as yes. If, for example, I say C2 equals coordinate, and then say 1 and 2, then here at line 7, when coordinate is being called here, passing 0 and 1, self, when doing line 7, self refers to C1. And when doing line 9, passing 1 and 2, x and y equals 1 and 2, when carrying out line 9, self refers to C2. These are instructions that are carried out on every instance of coordinate. And concerning what's the null, that be in reference to my silly example of creating additional attributes. Because if so, this is only to demonstrate that creating attributes on classes is as simple as declaring them on self in the init function. You can do this other ways, but I'm not going to talk about it because I don't recommend it. Best way to declare an attribute on a class instance is in the init function by just saying self dot and then naming the attribute and then assigning it some value. A couple more questions in the chat, all of which are spoilers on the exercises that I have planned. So that's great news. And in fact, yes, the question about calculating the norm and so on and so forth. Yes, absolutely. So defining methods on a class is how we do this. How we do, say, things like defining a norm method on a coordinate such that every time we call norm on one of our instances, it'll automatically calculate the norm of our coordinate based on, we've been saying it's internal data, in this case, based on the values of the attributes X and Y. So let's do it. And in this case, let's write our first actual method for doing some calculations. And for writing methods on classes, we define these in general in the same way as we defined functions, with the following two rules. First, as you see here in the init function, but now explicitly stated, when declaring the header of a class method, we do start with def, as in with normal methods, but again, while respecting the level of indentation of the class body. So again, everything one level of indentation up from the class header is considered part of the class body. And so in this case, if I say had def here, def my function, this is a function all on its own, whereas this is a method defined for the coordinate class. And so in this case, let's name our function distance, just like we would with any old function. And let's go ahead and start some parentheses to specify some arguments. And you'll notice with my IDE, if you're watching, my IDE will automatically, again, populate this method with the argument self. And that is because every class method can refer to itself. When we do things like call self dot, or say pop or remove or append on a list, each of those has a class method that refers to itself when carrying out whatever is defined for that particular method. And the reason that this is powerful is because when using self to refer to, just like in the init function, to refer to whatever the internal data is for a particular instance of this coordinate, the particularities of the instance is totally abstracted away. And instead, all we're thinking about here is not necessarily what an instance of the class, what its state is, but rather in general, what is the distance from, say, one instance of our coordinate to, say, another instance of our coordinate, without regard to the actual values, but just in terms of every coordinate has the attributes X and Y. We only have to think in those terms. And so if we want to say, define a method called distance on our coordinate object, and all of this function does is just takes as argument some other coordinate instance and returns the distance from itself to the other coordinate, we can do something like as follows. Say dx, call it dx2, which would be the square distance along the x coordinate. And let's do parentheses. We're going to refer to the x attribute of the instance of this class. whatever instance it is, the one that's called when someone is using our class, to refer to this instance's X attribute, self.x. And while we're at it, if we're going to compute the squared distance along the x-axis of whatever coordinate system this refers to, we can just say in our parentheses self.x minus other.x, assuming that other refers to some other instance of our coordinate class. And then square it. Now, if you're struggling with this concept for a second, just bear with me, follow along, and then we'll talk through this within the context of actual usage, and then maybe it'll be more clear. So for now, hang with me if you're struggling. Let's compute the rest of this. Let's fulfill this method definition, and then let's actually talk through this and see how this magic is happening. Let's do the square distance along some y-axis. We'll call that dy2 equals, and we'll say self.y, referring to the y attribute of this coordinate instance. And we'll subtract the value of the y attribute of some other coordinate, which is passed to this function as an argument. And then, you guessed it, we'll square it. And then let's do distance here by returning. And we'll do our square distance along the x direction plus our square distance along the y direction, and use the power operator to take the power of 0.5 to the square root. So this question, how is instance defined? So yeah, in the case of computer science, excuse me. So we have this distinction between the type of an object and an instance of a type. In that we are here defining a class, which is the definition of a type, and then we can create objects that consist of instances of that type. So C1 is an instance of the coordinate type, as is C2. Both are instances of the same type, but they are different objects. They may be instances of the same type, but each of them has a place in memory. In this case, each of them has the attributes x and y. They can have instance equals object type. No, instance is an object of a particular type. Maybe we're saying the same thing. I just want to make sure that we're clear. You know, so like, for example, did a lot of A equals 1, B equals 2. A and B are both instances of the int type. C1 and C2 are both instances of the coordinate type, and A, B, C1, and C2 are all objects. So an instance of a type is an object of that type. And maybe it seems a little pedantic, which I try to not do unless absolutely necessary. But in the case of relating the what occurs in the definition of a class compared to how it's actually used, tend to err on the careful side when it comes to the actual terminology that's being used. And maybe that'll be apparent here. So for those of you who stuck it out with me and defined this definition of a distance on this coordinate class, maybe some of you guessed it, but now I can come down here and for one of my coordinate instances, C1 or C2, I can say C1 dot distance. My IDE recognizes it. And what I don't pass is something for self. This is maybe the most confusing thing, the most, but the easiest way for people to get tripped up on how to actually implement class definitions, because there is this argument here for this class method for init and for distance. Both of these methods have the self argument. And yet, if C1 in this case is what's referred to by self, the natural question is, should I pass C1 as the first argument if I want self to refer to C1? Which is reasonable, except that what occurs here actually under the hood is that Python will automatically, without any intervention on your part, actually with the assumption that you won't do anything regarding this, Python will automatically interpret this as C1 being passed to the argument self. In which case, the first argument that we pass in this call will actually be the second argument that's passed to the method. The instance that is called will automatically be passed to self, and then all of the arguments with order respected will be passed as arguments after that. In which case, if I say C1.distance and passing C2, C1 is self in this case. When executing this instruction, C1 is self and C2 is other. In which case, maybe it's a little trivial now to see that both C1 and C2 are coordinate instances, which means they both have the attributes X and Y. In which case, if C1 is self and C2 is other, then we're just doing C1 minus X, or C1, its attribute value for X minus C2's value for X squared, same for Y, and then returning the square root of the sum of those distances. And when reversing the call, C2 dot distance of C1 when carrying out the instructions for line 17. Now C2, which is a coordinate instance, C2 is what's passed in as self, and C1 is now other, because both of them, being coordinate instances, have that method defined. Now let's do a poll again and see how we're doing with this. Because if we're gonna lose people, maybe this is the spot where it might happen, and I just want to make sure that it's at the end of the day and it's a fairly abstract concept, and so just want to make sure that we're at least on the same planet here. All right. While we're giving everyone time, Maria asks, is it possible to generate a list of these classes? You betcha, you sure can. class instances, just like ints and floats and everything else. They can be in lists, they can be in tuples, they can be in dictionaries, subject to the constraint that I mostly glossed over in our last module about the consideration of whether or not an instance is hashable. And we're not going to deal with that this week. So we're just going to neglect it for now. But in general, yeah, you can do my coordinates, say, is a list, and then for n in range of 10, and just say my coords and just append instances, say n and n plus 1, iterating from 0 up to 9 inclusive, and just creating a coordinate with the x value equal to n and a y value equal to n.1. That's created here, and then it's automatically appended to this list my coords. Similar operations for dictionaries, as we sort of crashed through in our last module. All of that is relevant to working with these custom class types. And maybe this seems a little off the deep end for some. And so if for those of you who may feel like this might be a little too computer sciencey, this is one of the most useful things for biological modeling, in that the class definitions that we write for Multicell are how we implement things like a cell definition. Diffusion fields, simulators, just about everything is formalized in some sort of class definition like this. One, to be able to organize the data well, and two, to be able to present something to users in an intuitive way. We just gave you a list with a bunch of like floats and strings with no coherent structure to it, then it would be pretty hard to work with. Whereas we can write, say, a class definition called cell and give it an attribute called volume. Now, that's not so random. That has some actual meaning to it. And that's what this is getting at, is that lots of the objects that we'll work with in this coming week is all defined in this same sort of paradigm, where the different objects that we work with, like cells or fields, they'll have attributes and they'll have methods defined on them, some of which can be used to interact with the simulation, some of which is used for the simulator to be able to report information back to you. So if you're struggling to see the relevance here because it is a bit abstract, I totally get that, and that's totally understandable. But maybe by the end of this coming week, maybe the relevance will hopefully be a little more obvious. Yeah, so with that in mind, you can do exercises like what I was just kind of typing through here, while giving everyone a chance to work through this, creating 2 instances, and you see calling this same method distance that we defined for our class, but we're calling it on different instances of that class, C1 and C2, and passing the other instance in this case. And so let's power on and work with this a little bit more. And yeah. And let's do some other useful things concerning class definitions, in particular, how to define interactions for some built-in methods like when we would call print on an integer, or say when we would call len on a list. There are special methods that you can define on a class that will tell Python how to respond to certain operations that are built in. And so in probably the simplest case, if we would like to say define, and we do this, to define what happens when we call, say, string on one of our coordinate instances, or if I try to say print one of my coordinate instances, print C1, and I get something here that mostly seems non-informative. Tells me the type of the instance and gives me some information about where it is in memory, but by and large, not very intuitive, not very helpful, for just basic usage. And so we can define another special function like init that will tell Python how to respond when, say, print is called on an instance of our class. We have lots of special built-in methods like this for some of the class definitions that we'll use this coming week. So in this case, if we want to tell Python what to do when string is called or when print is called, we can do this by defining a special method like init called str with, again, underscores before and after str. And this is a special method that takes only the argument of self, same self as every other method. It's referring to an instance. And we can do, say, the generation of some custom string based on the internal data of our class instance, and then return a string that reports that. We want to know, say, when we print a coordinate instance, what the actual values of x and y are, then we can here return a string that states what those values are. So we can do something like return and say str of self.x. This referring to the value of the attribute x on this particular instance when it's called. Say str of self.x, and again we can create strings from strings by using the plus operator or the addition operator. Say plus and then a string with a comma separating the string of self.x from the string of self.y. This is just instructions to tell Python what to do when someone calls str, like what we're doing here, calling string on self.x. That's only possible because this special method is defined for whatever data type, whether it be an int or a float, whatever type self.x may be. And we're going to make it possible for the coordinate class as well. So if you want to get fancy and make this maybe a little bit nicer, you can also say add some parentheses around the string that's generated. Let me expand my screen for just a moment so we can see everything that's going on here. And now I'm going to return to this call to print on an instance of a coordinate. And let's see what happens now. Again, it's implied here that C1 is converted to a string, and print does that automatically. And we'll find here that now when we print the instance of a coordinate, now we get this nice string that is just what's returned by this function. Now there's a lot of built-in methods like this that can define all sorts of operators for particular types. When we've done things like we consider the difference between adding two floats and adding two lists. In both cases, we can take two named variables and type a plus between them. And if they're two floats, then what's returned is the arithmetic summation of the two elements. Whereas if we say have two lists and we say one list plus another list, it's a totally different operation. And the operation being that the one list is added to the end of the other. And those operations can vary using the same symbols, just depending on what the types are involved in the operation. And for classes, this is all implemented using special built-in functions like what we did with str, but also doing instructions like telling Python what to do if, say, we wanted to add two coordinates. What does that mean? And of course, it means whatever the designer of the coordinate class says it does. But what's important here to recognize is that plus, minus, doing comparison operators, or taking len for different instances of different types can mean a lot of different things. And usually in these cases, we refer to documentation if using, say, Compusel. What did I or one of my predecessors or one of my colleagues define as being an len operator on a class? And these things are designed specifically to facilitate using these different types of abstractions for, say, doing things like what was mentioned in the chat. I say like defining coordinates within a blood vessel or something like that. And so as a last little exercise, and I would actually like to, let's go ahead and get that poll going, and I'll give everyone a couple of minutes to sort of get their head around this, make sure we're good with this. We can just skip doing some of these other built-in methods. I think that we can build some familiarity with that as we go throughout the week coming up. Or again, of course, if anyone's interested in learning some of the more, more of these details, I'd be more than happy to provide some resources for that and get you started in that direction. Great, I see comments in the chat about more details. It's music to the ears of a developer. Now it looks like we have a couple of responses of people who need help. And this seems like a persistent response lately. And what I'm afraid of is that maybe some people are just not following and not getting the help that they need. And so please, if you do need assistance with something, either reach out to one of us in private chat or raise your hand. We want to make sure that no one gets lost along the way, especially in this these last few minutes. Give everyone another minute or so. And we're gonna look at our last little bit. And then finish out with some question time. See, there's an issue with getting an error on str and coordinates. Oh, sorry about that. Yeah, so the important thing to note here is that when defining, say, the string method, and every built-in method like this has particular requirements, specifically because you're telling Python ways to interact with your class in a sort of standard way. In this case, for str, nothing gets passed to the function except self, which is done implicitly, and the only thing that can be returned is a string. All right. So in the last 10 minutes, I'm going to do just a very quick little crash course since we have very little time left. There are some, I would say, standard packages, depending on the application that you might be interested in. It's pretty much guaranteed that this week you'll get at least some exposure to a couple of packages that get used a lot in Compicell, one of them being NumPy, which is used in just about, I don't want to say every scientific computing application, but it's extremely common, which is used for mathematics, matrix operations, a lot of things to do with scientific computing. And another package called SciPy, which has a lot of, it's a great library with a lot of features, from everything to do with statistical analysis to optimization, all sorts of things. I've worked with those libraries for a while, and I still don't know everything about them. And so what my hope is for these last few minutes is to actually do a sort of crash course on some useful built-in features that are provided within the Python library, and more so get acclimated to using functions that are defined in other libraries, so that when we actually get to application time this coming week, it won't be such a foreign idea to say get a function from NumPy or from SciPy, import them into a script and start using them according to the documentation. So there are some standards for NumPy and SciPy. And for those of you who might be interested in learning about those between now and tomorrow, I can post a couple of walkthroughs for sort of crash courses on using NumPy. But for now, we're going to look at just some standards. So these are all built-in libraries that come with Python in particular. We do a lot of work with stochastic processes, lots of random number generating, and so on and so forth. And so for doing these sorts of operations, the go-to library, which you can import into your script, is just called random. And you can get this by just saying at the top of your script, import random. And now all of these functions are available. These are just a few, the ones that I tend to see used the most in Compicell-based modeling. So if, say, I want to get a uniformly distributed random variable in 0 and 1, you can say my randnum equals random.random. Now you'll notice here that I'm actually referring to the module that was imported in a similar way to how referring to methods on coordinate instances, and that's intentional. And that is to handle specifically cases like, what if, say, I had something else named random as well? How would I handle things like name clashes? Two libraries define functions with the same name. how do I use both of them in the same script? And the way that we can do this is through this sort of naming convention. So here, just calling the random function defined in the random module. And if you go and look in the documentation, you'll find that this function will return a random number in 0 and 1 according to a uniform distribution. And of course, you can follow along with the rest of these as denoted here. In particular, I would also like to bring to your attention for this module, for those of you who have not ever worked with pseudo-random number generators, these are not random numbers in a true sense, but they are pseudo-random. So they are predictable, and they are predictable according to what's called a seed. And the seed is what's used to generate the pseudo-random sequence of numbers that can be generated upon successive calls to functions like random.random. Most importantly, that if you provide to the random module, if you provide the same seed value to this function seed, and then call functions like random.random successively, you will get the same sequence. This is a repeatable set of floats or integers or what have you that you may be generating, but this is particularly important for generating stochastic simulations in a reproducible way, because if, say, we go to do some CompuCell simulations, and your simulation does something interesting, and then you may run it again and find that it does something different the second time. Another way to reproduce something that you've observed in a particular simulation is to use the same random seed, because the same random seed will produce the same stream of pseudo-random numbers. So to make your simulation reproducible, you can declare a seed and then pass it to random.seed. There's a way to respect that in CompuCell as well, and we can get into the details of that in the upcoming week. Same principle applies for CompuCell. We provide an interface to be able to do that. So I think Juliana will get into maybe tomorrow. Anyway, lots of other methods and many more than what's included here. Very quickly, there's the time module. And this is a way to be able to do things like pause your simulation. And this is built in, so you can say import time. And you can do things like pause your simulation for a number of seconds by calling time.sleep. And this will pause my software for 1 second, 10 seconds, 100 seconds, so on and so forth. You can do lots of other things like timing, taking time measurements to do like benchmarking to see how long something takes. This is all counted according to whatever your computer thinks is the beginning of time, which is called the epoch. That varies by platform. We can skip those details for now, and instead just remember that we can get the current time in integers using time.time. Say t1 equals time.time. The math library, we've already done this a little bit, but the math library provides a lot of basic math functionality. The name is just math. So as we did with square root earlier, import math. Lots of constants defined like pi, not a number, infinity, rounding functions, error functions, factorials, our square root, trig functions, inverse trig functions, so on and so forth. There's a basic statistics package for doing things that will be of interest to us this week, like calculating, say, the distribution of a random walk, quantiles for lots of simulation replicas doing the same simulation over and over and over, and quantifying the variability among replicas, things like that. You can use the statistics package for basic procedures, and then of course, as we may get into in this coming week, SciPy has a lot more available. And with that, we're at 1 minute left on the modules. So I'm going to leave this exercise up. I have a sample code generated for how to do this, but I'd like to just talk you through it very quickly before we start in on questions. This is a classic simulation of simulating a random walk. And so what occurs here is you pick a position as some variable in a 1D space. And so this variable defines a position for where something like a random walker is. And then just do a number of iterations, say 100,000 simulation steps in a for loop, and just generate random numbers at every iteration, and then test a certain probability, say 5%, that the random walker either increments its position by 1 or decrements it by 1. So if that's unclear, let's talk about it via email, which I think everyone has. I'll make that more clear. And again, I'll post the sample code as well. James, I'd like to turn it over to the general discussion now. So I'd like to turn it back to you, maybe stop talking for a minute. And yeah, thank you all again for being here and for sticking it out for this very brutal session of crash coursing through a lot of the basics of Python. It's been a real pleasure. And James, I'm really turning it over to you now.
Okay. Okay, well, there's nothing formally planned here. It was simply an opportunity to ask some questions. Please feel free to unmute. If you have trouble unmuting, just let us know and we can do it for you. If there are no questions, you certainly don't have to stay around, but it was more to make sure that everyone had the information that they needed. Just to remind you, tomorrow we're going to start again at 10 o'clock with a basic check-in and introduction. The formal modules will begin at 10:30, and we'll follow the same schedule as this week. If you need to talk to us, you have our contact information. And also, if you would like to participate in the hackathon, please do let us know. And if you're having any ideas or want things to discuss, let us know as well. If there are any questions from the things you want clarified? Noah, is there a question?
Well, I just need to do all the exercises because I haven't got the chance. I came in the middle, so yeah.
Okay, we'll try to pull the exercises out of the slide decks, but that may not happen immediately. It may take a day or two.
Okay.
But the slide decks are available, so you should have those in the student materials folder.
Just tell me which slides. Is it like 1 to 4 or 1 to 5? 1 until 5? I don't know. I mean, just give me the names of this specific slides, and then I look at them.
Oh, okay, right. So the each day is numbered. So today is day 0, and each module is numbered. So it's module 1, 2, 3, and 4. So it would be the introduction to Python would have been module 0.1.
Yeah.
The discussion of lists and strings was module 0.2. The discussion of dictionaries was 0.3. and the discussion of classes was 0.4.
Makes sense.
Then real quick, while we're pulling out the individual exercises to at least get started, all of the slides in those 4 slide decks, the ones that are actual exercises will say it really big across the top. So in the very least, you can grab those slide decks for now. And when you just click through the slides, you should be able to spot them pretty easily.
I think there may have been 1 or 2 other questions in the chat, if you wanted to look at those.
Do you listen to me?
Please go ahead.
Okay. I'd like to know for tomorrow, do we need to download something or register just to prepare the day of tomorrow?
So please register. That we're going to be teaching the course using the online version of Mutlicell. So please, can somebody paste the NanoHub link into the chat?
Mhm.
Let me get that for you. So if you were able to use the NanoHub, yeah. Sorry.
For NanoHub, I already did it, so I
Yep.
just
So
wanted to know if there's something else or we need to register something.
no.
Okay.
It should just be using this tool here. I mean, if you wanted to download Mutlicell onto your local computer, you can, but it's easier to start with to use the NanoHub version because then everybody sees the same thing. Any other questions or concerns? I know for some people coming from Europe, it's quite late, so you certainly don't have to stay on if you're tired. But we just wanted to make ourselves available to answer any questions.
I hope I can participate in the hackathon. I don't know.
Yes, you're welcome. So just let us know that you want to do that. You're welcome to participate. Okay, well, if there are no more questions, then I think we're done for today. I guess TJ and Giuliano, Jim, we should probably talk for a minute before 6, if it's possible. Lorenzo, thank you very much for showing up and helping out. And I look forward to seeing everybody tomorrow. I guess I'll see the team around 9:30, 9:45, and I'll see all of you between 10 and 10:30 tomorrow morning. Thank you for joining today, and look forward to working with you during the week. Good night.
Night, thanks.
I don't know how many people are left here. Okay.